The universe has countless stories, but each can be cracked open like a nut and retold in just a few words. Indeed, it is infinite or simply very vast, eternal or just long-lived. How can our limited minds grasp the concept of an infinite universe? Perhaps it is too presumptuous of us to even try. We have made significant progress in understanding the cosmos, especially in recent years. We do not yet have a complete picture, but perhaps we are not far from it. When it comes to space, its most obvious quality is that it stretches infinitely in all directions. This is confirmed by modern measuring instruments, such as the Hubble Space Telescope, which allows us to peer deep into the cosmos. We then see billions of galaxies of various shapes and sizes. Each galaxy contains countless billions of stars, and many of them have planets orbiting around them. We live on a planet that orbits a star in the outer spiral arm of the Milky Way. The dust in the spiral arms obscures our view in the plane of the galaxy, making it difficult for us to discern what is happening in the depths of the universe in that direction. However, in the cones on either side of this plane, we can see everything clearly, and we can determine the locations of distant galaxies. It turns out that galaxies are distributed throughout space more or less evenly, but there are local clusters and voids in some areas. The density of galaxies at very distant distances seems to decrease, but perhaps this is simply because we cannot distinguish very distant and faint galaxies. As far as we can tell, the universe extends infinitely in space, although it is roughly the same everywhere. Over time, it is definitely changing. This realization began to emerge only in the early years of the 20th century. Before that, it was believed that the universe was unchanging and could exist indefinitely. However, this led to absurd conclusions. If stars shine forever, they must have heated the universe to their temperature. Even at night, the sky would shine brightly like the sun, as all lines of sight would either hit a star or a cloud of dust heated to stellar temperatures. We all know that the night sky is dark, and this is a very important observation. It implies that the universe did not always exist in the state we see today. In the past, some finite time ago, something happened that ignited the stars, meaning that the light from very distant stars has not yet reached us. This explains why the night sky does not glow entirely. If stars had been sitting in their places forever, why did they suddenly ignite billions of years ago? What told them it was time to shine? As we have seen, this puzzled philosophers like Immanuel Kant, who believed that the universe existed eternally. However, for most people, this did not contradict the idea that the universe was created in roughly its current form a few thousand years ago. But in the second decade of the 20th century, instead of Slipher, Edwin Hubble conducted observations that indicated that the model of an unchanging universe was logically untenable. In 1923, Hubble discovered that many faint spots of light, known as nebulae, were actually other galaxies, vast clusters of stars similar to our Sun, but so distant that they appeared small and faint. The distance to them must have been so immense that the light from them traveled to us for millions or even billions of years. This means that the universe could not have originated just a few thousand years ago. Hubble then made a second, even more significant discovery. By analyzing the light from distant galaxies, one could determine whether they were moving toward us or away from us. To the astonishment of astronomers, it turned out that almost all galaxies are moving away from us. Moreover, The farther they are, the faster they are receding. It was Hubble who understood the astonishing implications of this discovery. On large scales, all galaxies are moving apart from each other, and the universe is expanding. The discovery of the expanding universe is one of the greatest intellectual breakthroughs of the 20th century. It was entirely unexpected and completely changed the course of the discussion about the origin of the universe. If galaxies are moving apart, it means that in the past, they were closer to one another. At the current rate of expansion, we estimate that 10 to 15 billion years ago, they were very closely packed. Stars ignited no earlier than 10 to 15 billion years ago, no earlier than the Big Bang. We are accustomed to thinking that observable events are caused by other, earlier events, and those by even earlier ones. The past stretches back in a long chain of cause and effect. But imagine that this chain has a beginning. Imagine that there was the very first event. What caused it? Scientists have approached this question with reluctance. They have tried to circumvent it, either by claiming, like Soviet scientists, that the universe had no beginning, or by asserting that the question of the universe's origin lies outside the realm of science and belongs to religion or metaphysics. If the laws of physics did not operate at the very beginning of the universe, why could they not fail at any other moment? If a law only works sometimes, it is not a law. We must strive to understand what the beginning of the universe was like, relying on scientific data. Perhaps this task is beyond our ability, but we are obliged to attempt it. It follows that the universe had a beginning, but they spoke little about the nature of that beginning. These theorems showed that the beginning of the universe was the Big Bang, a moment when the entire universe and everything in it was compressed into a point of infinite density. At this point, Einstein's general theory of relativity broke down and could tell us nothing about the beginning of the universe. It remained to conclude that the origin of the universe clearly lies outside the scope of science. But scientists should not be satisfied with such conclusions. General relativity does not apply at the moment of the Big Bang, and immediately afterward, as it does not include the principle of uncertainty, the random element of quantum theory, against which Einstein objected, believing that God does not play dice. The idea that the universe has many stories seems to belong to the realm of fantasy. However, nowadays it is considered a proven scientific fact. This hypothesis was proposed by Richard Feynman, a great physicist and a remarkable original thinker. Today, we are working to reconcile Einstein's general theory of relativity with Feynman's hypothesis of multiple histories of the universe into a single comprehensive theory that would describe everything happening in the universe. This grand unification model will allow us to calculate how the universe will evolve if we know how its stories began. However, the grand unification model alone will not tell us how the universe originated and what its initial state was. For that, we need what are called boundary conditions, rules that establish what happens at the boundaries of the universe, at the very edge of space and time. If the boundary of the universe were an ordinary point in space and time, we could cross it and declare the territory beyond it to be the backside of the universe. On the other hand, if the boundary of the universe were an uneven edge where space and time are compressed and density is infinite, it would be very difficult to define meaningful boundary conditions. Perhaps the universe has no boundaries in space and time. The history of the universe in imaginary time defines its history, and real time does the opposite. But these could be two entirely different histories. In particular, the universe in imaginary time does not need either a beginning or an end. Imaginary time behaves simply as another spatial dimension. Thus, the history of the universe in imaginary time can be envisioned as a curved surface, a sphere, a plane, or a saddle, but not with two dimensions, rather with four. If the histories of the universe extend infinitely, as they do on a plane or saddle-shaped surface, it is difficult to determine what the boundary conditions are at infinity. However, one can circumvent this obstacle and not define boundary conditions at all. If all histories of the universe in imaginary time are closed surfaces, like the surface of the Earth has neither boundaries nor edges. It seems that no one has ever fallen off it. If the histories of the universe in imaginary time indeed represent a closed space, this would require a fundamental revision of philosophy and our understanding of our own origins. In that case, the universe is completely self-sufficient. It does not need any external influences to start or set its mechanisms in motion. On the contrary, everything in the universe is determined by the laws of physics and the toss of dice within the universe itself. As presumptuous as it may sound, this is how the world appears to me and many other scientists. Even if the boundary conditions of the universe consist of it having no boundaries, the universe does not have just one history. It has many histories, as Feynman suggested. Each possible closed surface in the universe corresponds to a history in imaginary time, and each history in imaginary time defines a history in real time. Thus, the universe is replete with possibilities. What distinguishes the specific universe we live in from the multitude of all possible universes? Firstly, it can be noted that many possible histories of the universe did not reach the stage of galaxy and star formation, without which we could not have emerged. Although, of course, one cannot exclude the possibility that intelligent beings could arise and evolve without galaxies and stars, it is still unlikely. That is, the history in which we live is defined in part by the fact that we exist, beings capable of asking why the universe is the way it is. Consequently, it belongs to the minority of histories where galaxies and stars exist. Before us lies an example of the so-called Anthropic Principle. The Anthropic Principle states that the universe must be roughly as we observe it, because otherwise there would be no one to observe it. Many scientists dislike the Anthropic Principle because it is not very rigorous and seems to lack predictive power. However, it can be formulated precisely, and without that, it seems impossible to answer the question of the origin of the universe. Most of these histories do not imply the emergence of intelligent life. Such universes are either empty, or they exist for only a short time, or they are too warped, or they do not meet some other criteria. However, according to Richard Feynman and his idea of multiple histories, uninhabitable histories likely have a high probability. Moreover, it is not very important how many possible histories there are in which there is no place for intelligent beings. We are only interested in the multitude of histories in which intelligent life has arisen. An intelligent life does not necessarily have to resemble humans. Small green aliens would suffice. They might even be better than humans, who often do not behave very intelligently. As an example of the Anthropic Principle, let us consider the number of spatial dimensions. Everyday experience teaches us that we live in three-dimensional space, meaning we can describe the position of a point in space with three numbers, such as latitude, longitude, and height above sea level. But why is it three-dimensional? Why is it not 2, 4, or some other number of dimensions, as in science fiction? According to M-theory, space has 9 or 10 dimensions, with 6 or 7 of them compactified and very small. So, what remains? Only 3 large and practically flat dimensions. Why do we not live in a history where 8 dimensions are compactified and we only perceive the remaining 2? A 2-dimensional creature would have a hard time digesting food. Its digestive tract would go right through it, and the poor creature would split in half and fall apart. Therefore, 2 flat dimensions are insufficient for such a complex organism as intelligent life. On the other hand, if we had 4 or more nearly flat dimensions, the gravitational pull between 2 bodies would increase more rapidly as they approached each other. This means that planets would not have stable orbits around stars. They would either fall into their sun or drift off into the cold and darkness of interstellar space. Similarly, there would be no stable orbits for electrons and atoms, so matter as we know it would not exist. Thus, although the theory of multiple histories allows for any number of nearly flat dimensions, intelligent beings can only exist in histories with 3 flat dimensions. Only in such histories can there be someone to ask the question of why space has 3 dimensions. The simplest history of the universe in imaginary time is a sphere, like the surface of the Earth, but with 2 additional dimensions. It defines such a history of the universe in real time as we perceive it. The universe is the same at any point in space and expands over time. In this sense, it resembles the universe we live in, but the rate of expansion becomes very high and accelerates over time. Such accelerated expansion is called inflation, as it resembles how prices continuously rise, and the further you go, the faster they rise. It is generally believed that price inflation is bad. However, in the case of the universe, inflation is very beneficial. The rapid expansion smooths out all the bumps and irregularities that likely existed in the early universe. As it expands, the universe borrows energy from the gravitational field to create additional matter. The positive energy of matter is perfectly balanced by the negative energy of gravity, so the total energy equals 0. When the size of the universe doubles, both the energies of matter and gravity also double, but 2 times 0 is still 0. If only everything in banking were so simple. If the history of the universe in imaginary time were a perfectly round sphere, the corresponding history in real time would represent a universe that expands eternally with acceleration in an inflationary manner. While the universe is inflating, matter cannot condense into galaxies and stars, and life, let alone intelligent life like ours, cannot develop. So, although the ideas of multiple histories allow for histories of the universe in minimal time that represent ideal spheres, they do not interest us much. However, histories in imaginary time that represent slightly flattened spheres from the southern pole are much more relevant to us. In this case, the corresponding history in real time will first expand with acceleration, that is, according to the inflationary scenario, and then the expansion will slow down, allowing galaxies to form. For intelligent life to develop, the flattened state at the southern pole must be very small. This means that initially, the universe must expand incredibly rapidly. The record for monetary inflation was recorded in Germany between the world wars when prices rose billions of times. But the inflation in the early universe must have been at least a billion times stronger. Thanks to the principle of uncertainty, intelligent life in the universe could arise not in one, but in several histories. Among the histories in imaginary time, there is a whole family of slightly deformed spheres, each corresponding to a history in real time, where inflation of the universe occurs for a long time, but not indefinitely. Now one might ask, which of these permissible histories is the most probable? It turns out that the most likely histories are not entirely smooth. They have small bumps and dips. The bumps on the most probable histories are microscopic deviations from smoothness on the order of 100,000th of a part. But despite their minuscule size, we have managed to detect them as slight variations in the cosmic microwave background radiation coming to us from different parts of the cosmos. In 1989, the COBE satellite was launched, which mapped the sky in the microwave range. Different colors on this map denote different temperatures. However, the entire range from red to blue is only about 1/10,000th of a degree. But these variations between different areas of the early universe are sufficient for additional gravitational attraction to arise in denser regions, ultimately preventing them from expanding and causing them to collapse under their own weight, leading to the formation of galaxies and stars. So, at least in principle, the COBE map represents the imprint of all large-scale structures of the universe. How will the most probable histories of the universe compatible with the emergence of intelligent beings behave in the future? There seem to be many options, and it all depends on the amount of matter in the universe. If it exceeds a certain critical value, the gravitational attraction between galaxies will slow them down and ultimately prevent them from flying apart. They will then begin to fall into one another, and at the end of the universe's history in real time, there will be a chaotic collapse, a big crunch. If the density of the universe is below the critical value, gravity is too weak to prevent galaxies from flying apart forever. All stars will burn out. The universe will become increasingly cold and empty, but it will eventually end again, just not as spectacularly. In any case, the universe still has a good few billion years left. It is likely that the universe contains not only matter, but also what is known as vacuum energy, energy that is present even in seemingly empty space. According to Einstein's famous equation, E=mc2, vacuum energy is mass. This means it exerts a gravitational influence on the expansion of the universe. However, it is noteworthy that the effect of vacuum energy is opposite to that of matter. Matter slows the expansion of the universe and can ultimately stop it and reverse it, while vacuum energy, on the contrary, causes accelerated expansion, inflation. Essentially, vacuum energy acts like a cosmological constant, the very one that Einstein added to his original equation in 1917, when he realized that they did not allow for a solution reflecting a static universe. When Hubble discovered that the universe is expanding, the need to add another term to the equation fell away, and Einstein abandoned the cosmological constant, believing he had made a mistake. But it may turn out that he was not wrong at all. We now understand that quantum theory implies that space-time is full of quantum fluctuations. According to supersymmetric theory, infinite positive and negative energy from zero-point fluctuations of particles with different spins annihilate each other. However, one cannot expect that positive and negative energies annihilate each other with such precision that no minuscule finite amount of vacuum energy remains. The state of the universe is not supersymmetric. The only surprise is that vacuum energy is so close to zero that its existence was unnoticed until recently. This is probably another example of the Anthropic Principle. In a history where vacuum energy is higher, galaxies do not form. So there are no beings to ask why we observe exactly this amount of vacuum energy. The amount of matter and vacuum energy in the universe can be measured based on various observations. The results can be represented in a graph where the density of matter is plotted on the horizontal axis and vacuum energy on the vertical axis. A dashed line marks the boundary of the region where the development of intelligent life is possible. The results of observations of supernovae, clusters of galaxies, and cosmic microwave background radiation are shown on this graph as areas of complex shape. Fortunately, all of them intersect. If the density of matter and vacuum energy fall within this intersection, it means that the expansion of the universe has begun to accelerate again after a long period of deceleration. It seems that inflation is a law of nature. The relationship between the speed of a wave source and the wavelength recorded by a receiver is known as the Doppler effect. We observe it almost every day. Listen to how a plane flies overhead. As it approaches, the roar of the engine sounds higher, and when it flies past and disappears into the distance, the sound becomes lower. A higher sound corresponds to shorter sound waves, which have less distance between adjacent peaks and a higher frequency, the number of oscillations per second. The fact is that when the plane moves toward you, it emits each wave closer and closer to you, thus reducing the distance between the peaks. Similarly, if the plane is flying away from you, the wavelengths increase, and the sound you perceive becomes lower. The Doppler effect also applies to light waves. If the distance from Earth to a certain galaxy were constant, the characteristic lines in its spectrum would be located at standard places on the wavelength scale. However, if the galaxy is moving away from us, the waves will appear longer, stretched out, and the characteristic lines will shift to the red side. If the galaxy is moving toward us, the light waves will compress and shift to the blue side. In 1912, Slipher analyzed the light of 4 nebulae and found that 3 of them exhibited redshift, while Andromeda showed blue. From this, he concluded that Andromeda is moving toward us, while the other nebulae are moving away. In 1914, Slipher analyzed the light from another 12 nebulae, and all but 1 showed redshift. In 1914, Slipher presented his findings to the American Astronomical Society. This report was heard by Hubble. In 1918, Hubble also began to study nebulae. In 1923, Hubble discovered that spiral nebulae, including Andromeda, are other galaxies. In 1925, Slipher and other scientists continued to analyze the Doppler shifts. In 1925, the count was 43 redshifts against 2 blues. In 1929, while continuing to study the Doppler shifts and discovering that on large scales all galaxies are moving apart from each other, Hubble and Milton Humason announced their discovery. The universe is expanding. By analyzing the light from other galaxies, Edwin Hubble found in the 20s that almost all galaxies are moving away from us at a speed proportional to their distance from Earth, v. Yasar h0 r. This important observation, known as Hubble's law, shows that the universe is expanding, and the Hubble constant h0 sets the rate of expansion. The hot Big Bang. If general relativity is correct, Then the universe began with the singularity of the Big Bang at infinite temperature and density. As the universe expanded, the temperature of the radiation decreased. About 1/100th of a second after the Big Bang, the temperature was around 100 billion degrees, and the universe primarily contained photons, electrons, and neutrinos, the lightest particles and their antiparticles, as well as some protons and neutrons. In the next 3 minutes, as the universe cooled to about 1 billion degrees, protons and neutrons began to combine and form helium, hydrogen, and other light element nuclei. After hundreds of thousands of years, when the temperature dropped to a few thousand degrees, electrons slowed down enough for the light nuclei to capture them and form atoms. However, the heavier elements from which we are made, including carbon and oxygen, formed only billions of years later as a result of helium burning in the interiors of stars. The first to propose this picture of the universe, dense and hot at the initial stage of its existence, was George Gamow in 1948 in a paper he co-authored with Ralph Alpher, which made the outstanding prediction that the radiation produced at this hot early stage should persist to the present day. This prediction was confirmed in 1965 when physicists Arno Penzias and Robert Wilson detected cosmic microwave background radiation. Richard Feynman was born in New York, in Brooklyn, in 1918, and defended his dissertation under John Wheeler at Princeton University in 1942. Shortly after that, he was recruited to work on the Manhattan Project. There, he became famous for both his fiery character and his penchant for pranks. For example, he loved to crack ultra-secret safes in the Los Alamos laboratories, as well as for his remarkable scientific achievements. He became one of the principal authors of the theory of the atomic bomb. The essence of Feynman's character was an insatiable curiosity. This not only served as the driving force behind his scientific successes, but also inspired him to the most astonishing adventures, including deciphering Mayan scripts. After World War II, Feynman found a fundamentally new and very promising approach to quantum mechanics, for which he received the Nobel Prize in 1965. Feynman questioned the fundamental classical assumption that each particle has only one history. He proposed that particles move from place to place along all possible trajectories in spacetime. Feynman characterized each trajectory by two quantities. 1. Size, that is, the amplitude of the wave. 2. Phase, that is, the peak or trough. The probability that a particle will transition from point A to point B is calculated based on the sum of the waves associated with each of the possible trajectories between A and B. Nevertheless, everyday experience teaches that objects travel along some single trajectory between the starting and ending points. This corresponds to Feynman's hypothesis of multiple histories or multiple trajectories. As for large objects, his law assigning numerical characteristics to each trajectory leads to the conclusion that when considering the entire set of trajectories, all but one annihilate each other. In the motion of macroscopic bodies, only one of the infinite number of trajectories plays a role, and that is precisely the trajectory defined by classical Newtonian laws. The initial state of the system changes over time according to the laws of physics. For example, if you throw a stone, its subsequent motion is accurately described by the laws of gravity. However, based on these laws, it is impossible to predict exactly where the stone will land. To do this, we need to know the speed and direction in which it was thrown. In other words, we need to set initial conditions. boundary conditions, the motion of the stone. Cosmology attempts to describe the evolution of the universe based on the same laws of physics. But for this, we need to ask what the initial conditions of the universe were, so that we have something to apply these laws to. The initial state likely had a profound impact on the fundamental features of the universe, and perhaps even on the properties of elementary particles and interactions necessary for the emergence of biological life. One of the hypotheses, the no-boundary hypothesis, states that time and space are finite, forming a closed surface without boundaries, just as the surface of the Earth is finite in size but without limits. The no-boundary hypothesis is based on Feynman's idea of multiple histories, but now, instead of the history of a particle, the sum reflects all of spacetime, reflecting the history of the entire universe. The no-boundary conditions precisely allow us to restrict all possible histories of the universe to those variants of spacetime that have no boundaries in imaginary time. In other words, the boundary conditions of the universe consist of the absence of boundaries. Cosmologists are currently investigating whether the initial configuration is preferred according to the no-boundary hypothesis, possibly considering the weak anthropic principle, which generates exactly the universe we observe today. Roughly speaking, the anthropic principle states that we see the universe as it is, at least in part, because we exist. This viewpoint is diametrically opposed to the dream of a unified theory that unequivocally predicts everything in the world, within which the laws of nature are absolute, and the world is as it is because it cannot be otherwise. There are several versions of the anthropic principle. Some are weak to the point of triviality, while others are strong to the point of absurdity. Most scientists are reluctant to accept the strong version of the anthropic principle. However, some weak anthropic arguments are so useful that they are unlikely to be disputed. The weak anthropic principle explains the epochs and parts of the universe in which we might exist. For instance, the reason the Big Bang occurred around 10 billion years ago is that sufficient time must have passed since the universe's inception for certain stars to evolve. Otherwise, they would not have produced the chemical elements, like oxygen and carbon, from which we are made. A brief history of the theory of relativity. How Einstein laid the foundations for two fundamental theories of the 20th century, general relativity and quantum mechanics. Albert Einstein, the author of the Special and General Theories of Relativity, was born in 1879 in Germany, in the city of Ulm, but his family moved to Munich a year later, where his father, Hermann, and uncle supposedly founded a small and not very prosperous electrical equipment trading company. In his childhood, Albert did not show much promise. However, rumors about his poor performance in school seem to have been exaggerated. In 1894, his father's business failed, and the family relocated to Milan. His parents decided that Albert should stay in Munich to finish school, but he disliked such despotism and left school after a few months to join his parents in Milan. Later, Einstein completed his education in Zurich. In 1900, he graduated from the prestigious Polytechnic, the Polytechnic Institute. By nature, Albert was a debater and did not recognize authority, which is why he did not earn much affection from his professors at the Polytechnic, and he was not offered a position as an assistant, which would have marked the beginning of his scientific career. 2 years later, Albert did secure a minor position at the Swiss Patent Office in Bern, and in this role, in 1905, he published 3 papers that made him one of the most outstanding scientists of modern times and initiated 2 conceptual revolutions that changed our understanding of time, space, and reality itself. By the end of the 19th century, scientists were convinced they were on the verge of fully describing the universe. They assumed that space was filled with a medium called ether. It was believed that light rays and radio signals were waves in the ether, similar to how sound is waves of compression in the air. The theory was missing just one small detail: an accurate measurement of the ether's elasticity. Moreover, when Harvard University was constructing the Jefferson Laboratory, it was intentionally built without a single iron nail to allow for precise magnetometric studies in the future. However, the architects forgot that the red-brown bricks used to build the laboratory and almost all of Harvard contained a lot of iron. The building is still in use today, and experiments conducted did not confirm this hypothesis. The most thorough and precise experiment was conducted by Albert Michelson and Edward Morley from the Case School of Applied Science in Cleveland, Ohio. In 1887, Michelson and Morley compared the speeds of 2 perpendicular beams of light. The Earth rotates on its axis and moves in orbit around the Sun, so the measuring instrument moves through the ether at different speeds and in different directions. However, Michelson and Morley found no difference in the speeds of the 2 light beams. It did not accumulate over a day or a year, as if light always traveled at the same speed relative to the observer, regardless of the direction or speed of the observer's movement. Based on the Michelson-Morley experiment, Irish physicist George Fitzgerald and Dutch physicist Hendrik Lorentz proposed that bodies moving through the ether behave as if light spreads in different directions at different speeds. This would mean that the maximum of the first light wave would reach its endpoint at the same moment as the minimum of the second light wave, causing these waves to cancel each other out. However, Einstein, in a paper written in June 1905, pointed out that if an observer cannot determine whether they are in motion or at rest, the idea of ether is superfluous. Einstein posited that the laws of physics should remain the same for all freely moving observers. In particular, the measured speed of light should be the same for all, regardless of the speed of the observers themselves. The speed of light does not depend on their motion and is the same in all directions. For this, it was necessary to abandon the notion of universal time, which all clocks measure. Time is personal. The time for 2 people coincides if they are at rest relative to each other, and does not coincide if they are in motion. This was confirmed by a series of experiments, including one involving 2 precise clocks that circled the globe in opposite directions and showed slightly different times upon their return. Thus, if you want to live longer, you should try to fly east so that the speed of the airplane adds to the speed of the Earth's rotation. However, the gain of a microscopic fraction of a second is more than offset by the unhealthy airplane food. Einstein's postulate that all laws of nature must be the same for all freely moving observers laid the foundation for the theory of relativity, named so because it implies that only relative motion matters. The beauty and simplicity of the theory of relativity convinced many thinkers, but it also had its opponents. Einstein refuted 2 unbreakable axioms of the 19th century: the axiom of absolute rest, exemplified by the ether, and the axiom of universal time, measured by all clocks. Many were displeased by this. They questioned whether Einstein's theory implied that everything is relative and that there are no absolute moral standards in the world. Doubts about the theory of relativity persisted in the 20s and 30s. In 1921, Einstein received the Nobel Prize in Physics for another important paper, which, by Einstein's own standards, was not as significant, also published in 1905. The theory of relativity was not mentioned in the Nobel Committee's motivation because it was considered too controversial. Nevertheless, today, the scientific community has fully accepted the theory of relativity, and its predictions have been verified by various experiments and are utilized in modern technology. One of the most important consequences of the theory of relativity is the relationship between mass and energy. From Einstein's postulate that the speed of light is constant regardless of the observer, it follows that moving faster than light is impossible. This is why, when someone expends energy to accelerate an object, mass and energy are equivalent, as shown in Einstein's famous equation, E equals mc squared. Energy equals mass multiplied by the square of the speed of light in a vacuum. This is probably the only equation in physics that everyone recognizes at first glance. One consequence of this equation is that if a uranium nucleus splits into two nuclei, the total mass of which is slightly less, a tremendous amount of energy is released. In 1939, on the eve of World War II, several scientists who understood the potential consequences convinced Einstein to abandon his pacifist beliefs and excessive scruples and to sign a letter to President Roosevelt, stating that the United States should initiate a nuclear research program. Einstein's authority lent significant weight to this letter. As a result, the Manhattan Project was launched, and bombs were created that were dropped on Hiroshima and Nagasaki in 1945. Sometimes, Einstein is blamed for this, as he discovered the connection between mass and energy, but that is akin to blaming Newton for airplanes crashing since he discovered gravity. Einstein did not personally participate in the Manhattan Project and was horrified when he learned about the atomic bombings. After his revolutionary papers of 1905, Einstein established a solid reputation in scientific circles, but he was not offered a position at the University of Zurich until 1909. Only then could he leave the Swiss Patent Office. 2 years later, he moved to a German university in Prague, but in 1912, he returned to Zurich, this time to the Polytechnic. Despite the widespread anti-Semitism in Europe at the time, even in universities, Einstein became highly sought after in the academic community. He was invited to Vienna and Utrecht, but he chose to take a position as a researcher at the Prussian Academy of Sciences, as it freed him from teaching duties. In April 1914, he moved to Berlin, where his wife and 2 sons soon joined him. However, the couple's relationship had long been strained, and soon the Einstein family returned to Zurich. Einstein occasionally visited them, but ultimately divorced his wife. Later, Einstein married his cousin Elsa, who lived in Berlin. It is possible that the years of World War I were particularly fruitful for him scientifically, partly because he was living a bachelor life and was not burdened by domestic responsibilities. Although the theory of relativity aligns well with the laws governing electricity and magnetism, it contradicts Newton's law of universal gravitation. According to this law, if the distribution of matter in a certain region of space changes, the change in the gravitational field is felt instantaneously throughout the universe. This not only implies that signals could be transmitted faster than light, which the theory of relativity prohibits, but also requires the existence of an absolutely universal time. Otherwise, it is unclear what instantaneously means, which the theory of relativity rejects in favor of local time. Einstein realized this complication in 1907 while still working at the patent office in Bern. But he did not seriously consider the problem until 1911, when he had already moved to Prague. He understood that there is a close relationship between acceleration and the gravitational field. An observer in a closed cabin, for example, in an elevator, cannot tell whether the cabin is at rest in the Earth's gravitational field or accelerating upward in a rocket in space. Of course, this was before the era of Star Trek, so Einstein envisioned not spaceships, but elevators. However, one can only accelerate or fall freely in an elevator for a short time. Otherwise, a catastrophe will occur. If the Earth were flat, one could equally claim that the apple fell on Newton's head due to gravity, or because Newton was accelerating upward with the Earth's surface. However, on a round Earth, acceleration and gravity are not equivalent. People on opposite sides of the globe would have to accelerate in opposite directions while remaining at a constant distance from each other. However, upon returning to Zurich in 1912, Einstein had an epiphany. He realized that acceleration and gravity on a sphere would remain equivalent if the geometry of spacetime were not flat, as previously thought, but curved. According to Einstein, mass and energy curve spacetime, but how they do this still needed to be determined. All bodies, both apples and planets, strive to move in spacetime in a straight line, but their trajectories are bent by the gravitational field because spacetime is curved. With the help of his friend Marcel Grossmann, Einstein studied the theory of curved spaces and surfaces developed by Georg Friedrich Riemann in the mid-19th century. However, Riemann only considered curved space. It took Einstein to realize that all of spacetime is curved. In 1913, Einstein and Grossmann co-authored a paper proposing the hypothesis that what we perceive as gravitational forces are simply manifestations of the curvature of spacetime. However, Einstein made a mistake in one aspect. It is human nature to err, so he and Grossmann were unable to derive an equation that linked the curvature of spacetime with the mass and energy contained within it. Einstein continued to work on this problem in Berlin. The war hardly affected him. He was free from domestic responsibilities, and in November 1915, he finally derived the necessary formulas. In the summer of 1915, he visited the University of Göttingen, where he discussed his ideas with mathematician David Hilbert, and it turned out that Hilbert had independently derived the same equations a few days before Einstein. However, as Hilbert himself acknowledged, the credit for the discovery of the new theory ultimately belongs to Einstein, as it was he who proposed linking gravity with the distortion of spacetime. It is worth noting that in those years it was quite remarkable, very civilized, that even during wartime the state did not hinder such scientific debates and communication among scientists. What a contrast to the fascist dictatorship that emerged 20 years later. The new theory of curved spacetime was named general relativity to distinguish it from the original theory, which did not mention gravity. We refer to that as special relativity. General relativity received striking confirmation in 1919 when a British expedition in West Africa observed a slight bending of light from a star passing near the sun during an eclipse. This was direct evidence of the curvature of space and time, which forced us to radically reconsider our perception of the universe. It can only be compared to the revolution in thought brought about by Euclid when he wrote his Elements of Geometry around 300 years before our era. With his general theory of relativity, Einstein transformed space and time from mere passive backdrops for various events into active participants in the dynamics of the universe. This brought us to a monumental question that occupies a central place in 21st century physics. Is the universe full of matter? And does that matter curve space-time in such a way that bodies are attracted to each other? Einstein discovered that his equations had no solutions that described a static universe, unchanging over time. Nevertheless, he did not abandon the idea of such an eternal and unchanging universe, which he and most of his contemporaries envisioned, but modified his equations by adding a term called the cosmological constant, which, by curving space-time in the opposite direction so that bodies would repel each other, was meant to balance the attraction of matter. Thus, the equations allowed for solutions that permitted the existence of a static universe. This was one of the greatest missed opportunities in the history of theoretical physics. Had Einstein adhered to his original equations, he would have predicted that the universe was either expanding or contracting. In any case, no one took the hypothesis of a time-varying universe seriously. However, by the 20s of the last century, sensational observations were made with the 100-inch telescope at the Mount Wilson Observatory. These observations showed that the farther away other galaxies are from us, the faster they are receding. The universe is expanding, and the distance between any two galaxies is constantly increasing over time. This discovery rendered the cosmological constant unnecessary. It turned out that Einstein's equations should not have a static solution. Subsequently, Einstein referred to the cosmological constant as the greatest blunder of his life. However, today it seems that it was probably not a mistake at all. The general theory of relativity completely changed the course of the discussion about the origin and fate of the universe. A static universe could have existed forever, or could have been created in its current form at some point in the past. But if galaxies are moving away from each other, it means that at one time they were closer together. About 15 billion years ago, they were literally piled on top of one another, and the density of the universe was extremely high. The Catholic priest Georges Lemaitre, who first explored this initial state of the universe, referred to it as the primeval atom, and it is now called the Big Bang. Einstein apparently never took the Big Bang theory seriously. Given the amount of light elements we observe in the surrounding world, the density would have to be at least 10 tons per cubic inch, and the temperature would be 10 billion degrees. Moreover, studies of cosmic microwave background radiation indicate that at one time, the density was likely a trillion units and 72 zeros tons per cubic inch. Furthermore, we now know that Einstein's general theory of relativity does not allow for the universe to abruptly transition from a compression phase to its current expansion phase, so Einstein's theory indeed suggests that time had a beginning, although he disliked that idea even more. He wanted to acknowledge that general relativity also predicts the demise of massive stars when they can no longer generate enough heat to counteract the force of their own gravity, which tries to compress them. Einstein believed that such stars fall into some stable final state. But today, we know that stars with more than 2 solar masses do not have any final state. Such stars continue to collapse and turn into black holes, regions of spacetime that are curved so much that not even light can escape from them. However, both the beginning and the end of time are points at which the equations of general relativity do not work. Thus, the theory does not predict what results from the Big Bang. Some see in this a manifestation of divine will, that God wanted and created the universe. But there are also those, including myself, who believe that the birth of the universe should obey the same laws that apply at other times. General relativity breaks down at the moment of the Big Bang because it contradicts the quantum hypothesis, the second great conceptual revolution of the early 20th century. The first step toward creating the quantum hypothesis was taken in 1900 in Berlin, when Max Planck discovered that the radiation from a red-hot body could only be explained if light is emitted and absorbed in discrete packets, now known as quanta. In one of his fundamental papers, written in 1905 while working at the Patent Office, Einstein showed that Planck's quantum hypothesis likely explains the so-called photoelectric effect. Some metals emit electrons when exposed to light. Modern light sensors and cameras are based on the photoelectric effect, and it was for this work that Einstein received the Nobel Prize in Physics. Einstein continued to develop the quantum hypothesis in the 20s, but he was deeply troubled by the work of Werner Heisenberg in Copenhagen, Louis de Broglie in Cambridge, and Erwin Schrödinger in Zurich, which was leading to a new picture of reality: quantum mechanics. Elementary particles lost their definite position and speed. The more accurately one could determine a particle's position, the less accurately its speed could be determined, and vice versa. This randomness and unpredictability of fundamental laws of nature frightened Einstein, and he never reconciled himself with quantum mechanics. He ultimately expressed his feelings in the famous aphorism, "God does not play dice." However, most scientists accepted the validity of the new quantum laws, as they could explain a range of mysterious phenomena. Moreover, they were well supported by observations. The laws of quantum mechanics form the basis of modern understanding in chemistry, molecular biology, and electronics, and initiated the technological progress that transformed the world over the next 50 years. In December 1932, realizing that the Nazis led by Hitler were about to come to power, Einstein left Germany and 4 months later renounced his German citizenship. He spent the last 20 years of his life at the Institute for Advanced Study in Princeton, New Jersey. Meanwhile, in Germany, the fascists launched a campaign against Jewish science and repressed many Jewish scientists. Partly for this reason, Germany was unable to develop an atomic bomb. One of the main targets of this campaign was Einstein and his theory of relativity. When Einstein was informed that a book titled 100 Authors Against Einstein had been published, he remarked, "Why so many? If I were wrong, one would be enough." After World War II, Einstein urged members of the anti-Hitler coalition to create a world government to control nuclear weapons. In 1948, he was offered the position of president of the newly formed State of Israel, but he declined. He once remarked, "Politics is ephemeral, but formulas are eternal." The formulas of general relativity are the best epitaph for Einstein and the best memory of him. They will endure as long as the universe itself. History has never known a period when the world changed so dramatically in just 100 years. It is not about new political doctrines, but about the rapid scientific and technological progress made possible by the achievements of fundamental physics. And the most fitting symbol of this progress is Albert Einstein. According to the theory of relativity, each observer measures time according to their own. This leads to the so-called twin paradox. One of a pair of twins travels into space at a speed close to the speed of light, while his brother remains on Earth. Due to the motion, time in the spacecraft passes more slowly than from the perspective of the twin left on Earth. So upon his return, the space traveler will find that his brother is now older than he is. At first glance, this contradicts common sense, but a series of experiments has shown that in such a scenario, the traveling twin will indeed be older. A somewhat prophetic letter from Einstein to President Roosevelt in 1939, thanks to the work of Joliot in France, as well as Fermi and Szilard in America, made it clear in the last 4 months that a chain nuclear reaction could be initiated in a large mass of uranium, resulting in the production of a great deal of energy and a large number of new elements similar to radium. It is now almost certain that this will be achieved in the near future. This new phenomenon will also lead to the creation of bombs, and one can speculate, though with much less certainty, that this will result in the creation of extremely powerful bombs of a new type. The binding energy of atomic nuclei consists of protons and neutrons held together by strong interactions. However, the mass of the nucleus is always less than the sum of the masses of its individual protons and neutrons. The difference in masses serves as a measure of the binding energy of the nucleus that holds it together. This energy can be calculated using Einstein's formula. The binding energy of the nucleus equals dm multiplied by c squared, where dm is the difference between the mass of the nucleus and the sum of the masses of its constituent particles. Nuclear explosive devices possess such destructive power precisely because of the release of this potential energy. A chain reaction of neutrons produced by the decay of uranium-235 collides with another nucleus. As a result, this nucleus also decays, initiating a chain reaction of further collisions. If the reaction sustains itself, it is called critical, and the mass of uranium-235 is referred to as the critical mass. Why do black holes, by absorbing information, prevent us from predicting the future? People have long wanted to control the future, or at least predict it. That is why astrology is so popular. Astrology claims that events on Earth are linked to the movements of planets in the sky. This hypothesis can be scientifically tested. More precisely, it could be if astrologers had the courage to make clear predictions that could be verified. However, they proceed cautiously and formulate their forecasts so vaguely that they can apply to any outcome. A statement like, "Tension in relationships with loved ones is possible," or "Don't miss the opportunity to improve your financial situation," cannot be disproven. However, the real reason most scientists do not believe in astrology is not the scientific data, or the lack thereof, but its inconsistency with other theories that have been experimentally verified. When Copernicus and Galileo discovered that planets move in orbits not around the Earth, but around the Sun, and Newton formulated the laws governing their motion, astrology quickly lost its credibility. Why should the position of planets against the backdrop of the sky, from the perspective of an earthbound observer, have any connection to macromolecules on one little planet that call themselves intelligent life. Yet this is what astrology convinces us of. The success of Newton's laws and other physical theories led to the idea of scientific determinism, first articulated in the early 19th century by the French scientist Marquis de Laplace. He proposed that if we knew the position and speed of all particles in the universe at a given moment in time, the laws of physics would allow us to determine the state of the universe at any other moment, both in the past and in the future. In other words, if scientific determinism holds true, we should be able to predict the future without any astrology. In practice, of course, even the simplest theory, like Newton's laws, gives rise to equations that we cannot solve for a system consisting of more than two particles. Moreover, often the equation exhibits a quality we call chaos, where tiny changes in position or speed at one moment can lead to enormous changes in the behavior of the system in subsequent moments. Anyone who has seen Jurassic Park knows that a tiny change in one place can cause colossal changes in another. A butterfly flapping its wings in Tokyo can cause rain in New York's Central Park. The problem is that this sequence of events cannot be repeated. When the butterfly flaps its wings next time, many other factors will be different and will affect the weather in an entirely different way. This is why weather forecasts are so unreliable. Thus, although the laws of quantum electrodynamics should, in principle, allow us to calculate everything in chemistry and biology, we have not made much progress in predicting human behavior using mathematical equations. Nevertheless, despite the practical difficulties, most scientists find solace in the thought that the future is, in principle, predictable. At first glance, it seems that the uncertainty principle poses a threat to determinism, as it states that we cannot accurately measure both the position and speed of a particle simultaneously. The more precisely we measure the position, the less accurately we can measure the speed, and vice versa. Laplace, in his version of scientific determinism, stated that if we know the position and speed of particles at a given moment, we can determine their position and speed at any moment in the future. But where to start if the uncertainty principle does not allow us to know both position and speed at the same time? No matter how powerful our computer is, if we input faulty data, we get faulty predictions. However, determinism has been restored to its rights by slightly altering it within the framework of the new theory of quantum mechanics, which takes the uncertainty principle into account. Roughly speaking, in quantum mechanics, one can accurately predict half of what the classical version of Laplace promises us. From the perspective of quantum mechanics, a particle does not have a precisely defined position and speed. Instead, its state can be described by a so-called wave function. The wave function is a number at each point in space corresponding to the probability that a particle will be found at that location. The rate of change of the wave function from point to point indicates how likely different speeds of the particles are. Some wave functions at a certain point in space have a sharp peak. In such cases, the uncertainty of the particle's position is very small, but it is also visible on the graph that in such cases, the wave function rapidly changes upwards on one side and downwards on the other. This means that the probability distribution for speed has a large range, indicating that the uncertainty in speed is high. Now let us consider a continuous sequence of waves, a wave packet. Here, the uncertainty of position is high, while the uncertainty of velocity is low. Thus, describing a particle using a wave function does not imply an exact description of its position or velocity. It adheres to the uncertainty principle. Now we understand that we can only accurately define one thing, the wave function. We cannot even assume that a particle has a position and velocity known to God, but hidden from us. Such hidden variable theories predict results that do not match observations. Even God is subject to the uncertainty principle and cannot know both speed and position simultaneously. He only knows the wave function. The rate of change of the wave function over time is governed by the so-called Schrödinger equation. If we know the wave function at a given moment, we can use the Schrödinger equation to calculate it at any other moment, in the past or future. Therefore, even in quantum theory, there is determinism, albeit reduced. We can only predict the wave function, not position and velocity simultaneously. This allows us to predict either position or velocity, but not both accurately. In other words, in quantum theory, the ability to make precise predictions is exactly half of what classical worldview suggests. Yet within this framework, it is still possible to assert that determinism exists. However, applying the Schrödinger equation to calculate the evolution of the wave function over time, that is, to predict what will happen in the future, essentially assumes that time flows smoothly and eternally everywhere. In Newtonian physics, there undoubtedly exists absolute time, meaning that each event in the history of the universe is assigned a label called time, and a sequence of such labels flows smoothly from infinite past to infinite future. It seems that this is how time appears from the perspective of common sense, and this picture of time exists in the minds of most people and even most physicists. However, as we already know, in 1905, the concept of absolute time was disproved by the Special Theory of Relativity, where time ceased to be an independent quantity and became simply one of the dimensions of the four-dimensional continuum known as spacetime. In the Special Theory of Relativity, different observers moving at different speeds traverse spacetime along different trajectories, and each measures time along their own trajectory. Moreover, different observers obtain different intervals of time between the same events. Thus, in the Special Theory of Relativity, there is no single absolute time that we can use to label events. However, the spacetime of the Special Theory of Relativity is flat, which means that within the framework of the Special Theory of Relativity, time measured by a freely moving observer smoothly increases in spacetime from minus infinity in the infinite past to plus infinity in the infinite future. We can apply all these measures of time in the Schrödinger equation to track changes in the wave function. So within the framework of the Special Theory of Relativity, we still possess a quantum version of determinism. In general relativity, the situation is different, as spacetime is curved and distorted by the matter and energy contained within it. In our solar system, the curvature of spacetime is quite small, at least on a macroscopic scale, so it does not affect our perception of time. In this situation, we can still rely on this time in the Schrödinger equation to obtain a deterministic evolution of the wave function. However, as soon as we accept that spacetime is curved, we open the door to the possibility that spacetime has a structure that does not allow time to increase smoothly in any reference frame, as we would like to think. For example, suppose that spacetime takes the form of a vertical cylinder. Time is plotted along the height of the cylinder, increasing from minus infinity to plus infinity from the perspective of any observer. Now imagine that spacetime has the shape of a cylinder with a handle, a wormhole, that branches off and then re-enters. Then any measurement of time will inevitably yield stagnation points where the handle enters the main cylinder, points where time stands still. At these points, time does not increase from the perspective of any observer. In such a spacetime, it is impossible to deterministically calculate the wave function in the future using the Schrödinger equation. Beware of wormholes. You never know what might come out of them. The reason we believe that time increases for all observers is due to black holes. They were first discussed in 1783. Jean Michel, a former Cambridge lecturer, reasoned as follows: if you launch an object, such as a cannonball, vertically upwards, its ascent will slow due to gravity, and eventually the object will stop moving upwards and fall back down. However, if the initial vertical speed exceeds a critical value, the second cosmic velocity, the gravitational force will not be sufficient to stop the object, and it will escape. The second cosmic velocity, or escape velocity, for Earth is about 12 kilometers per second, and for the Sun, it is about 618 kilometers per second. These escape velocities are much higher than the speed of a typical cannonball, but they are very small compared to the speed of light, 300,000 kilometers per second. This means that light escapes from Earth without much difficulty. However, Michel noted that there must be stars much more massive than the Sun, for which the second cosmic velocity exceeds the speed of light. We cannot see these stars because all the light they emit is pulled back by the star's gravity. Michel called such stars dark stars, and we refer to them as black holes. Michel's hypothesis of dark stars was based on Newtonian physics, in which time is absolute and moves forward regardless of anything. Therefore, in the classical and Newtonian picture, dark stars did not hinder our ability to predict the future. However, in general relativity, where massive bodies curve space-time, everything is quite different. In 1916, shortly after Einstein proposed his theory, Karl Schwarzschild, shortly before his death, he died from an illness contracted in Russia during World War I, found a solution to the equations of general relativity that described a black hole. For many years, scientists did not understand the essence or importance of Schwarzschild's discovery. Einstein himself never believed in black holes, and his view was shared by most of the old guard of specialists in general relativity. In 1963, quasars were discovered, which triggered an avalanche of theoretical work on black holes and experimental attempts to observe them. The picture that emerged is as follows. Consider the evolution of a star with a mass 20 times that of the Sun. Such stars form from gas clouds, like those found in the Orion Nebula. Gas clouds collapse under their own gravity. The gas heats up, and eventually it becomes so hot that a thermonuclear fusion reaction is initiated, converting hydrogen into helium. The heat generated in this process creates pressure that helps the star resist its own gravity and prevents it from collapsing further. In this state, a star can remain for a long time, burning hydrogen and emitting light into space. The gravitational field of the star affects the trajectories of the light rays emitted from it. One can draw a graph where time is plotted on the vertical axis and distance from the center of the star on the horizontal axis. On this graph, the surface of the star is represented by two vertical lines on either side of the center. Let us agree that time is measured in seconds, and distance is measured in light seconds. This is the distance light travels in 1 second. When using such units, the speed of light equals 1, meaning that the speed of light is 1 light second per second. This means that far from the star and its gravitational field, the trajectory of a light ray on this graph represents a line at a 45-degree angle to the vertical. However, closer to the star, the curvature of spacetime caused by the star's mass alters the trajectories of the light rays, and the angle to the vertical becomes smaller. Massive stars burn hydrogen into helium much faster than the sun. This means that after just a few 100 million years, they will run out of hydrogen. After this, such stars find themselves in a crisis. They can burn their helium and convert it into heavier elements, such as carbon and oxygen. However, during such nuclear reactions, less energy is released, and stars lose heat, along with the thermal pressure that helps them resist gravity. Therefore, they shrink. If their mass is more than twice that of the sun, the pressure will not be sufficient to halt the collapse. Such stars will collapse to zero size and infinite density, resulting in what is known as a singularity. On the diagram showing the relationship between time and distance from the center of the star, it is evident that as the star collapses, the trajectories of the light rays emitted from its surface emerge at smaller angles to the vertical. When the star reaches a certain critical radius, the trajectory on the graph becomes vertical, meaning that light will be suspended at a constant distance from the center of the star, but will not escape outward. The critical trajectory of light defines the surface of the so-called event horizon, which separates the region of spacetime from which light can still escape from the region from which it can no longer be emitted. Any light emitted by the star reaches the event horizon, but there the curvature of spacetime bends it back toward the star. Such a star becomes a dark star, according to Maxwell, or, as we say today, a black hole. How can one detect a black hole if no light can escape from it? The answer is that a black hole exerts the same gravitational force as the star from which it collapsed, and this force affects neighboring objects. If the sun were to become a black hole and manage not to lose any mass, the planets would orbit around it just as they do now. Therefore, to find a black hole, one can, in particular, look for matter that orbits around an invisible compact massive object. Scientists have observed a number of such systems. Perhaps the most striking are the giant black holes found at the centers of galaxies and quasars. All the properties of black holes that we have discussed so far do not create particular obstacles for determinism. For an astronaut caught in a black hole and confronted with a singularity, time will stop. However, in general relativity, one can measure time differently in different locations. So it is possible to speed up the astronaut's clock as they approach the singularity, and they intend to experience infinite time. On the time and distance diagram, surfaces of constant time values accumulate at the center below the point where the singularity appears, but they do not align with the usual time measurement in nearly flat spacetime far from the black hole. This time can be introduced into the Schrödinger equation to calculate the evolution of the wave function, meaning that determinism still exists. But it is of no use since later on, part of the wave function will be trapped inside the black hole, and it will be impossible to observe it from the outside. In other words, an observer who has the sense not to fall into a black hole will not be able to determine what the wave function was in the past using the Schrödinger equation. For this, they would need the part of the wave functions that is contained within the black hole. There is potentially a vast amount of information there, as a black hole with a specific mass and rotation speed can form from a very large number of different sets of particles. A black hole does not depend on the nature of the body from which it formed due to collapse. In this regard, John Wheeler said, "A black hole has no hair." The French have solidified their suspicions. The difficulties with determinism began when I discovered that black holes are not entirely black. Quantum theory asserts that fields cannot be exactly zero, even in a vacuum. If they were zero, they would have an exact position of zero, and an exact measure of either position or speed also being zero, which would violate the uncertainty principle that states one cannot precisely determine both position and speed. All fields must instead have a certain amount of so-called zero-point fluctuations. Zero-point fluctuations can be interpreted in several ways. At first glance, they appear different. However, mathematically, they are equivalent. From the perspective of positivist philosophy, one can use any picture if it helps solve a particular problem better than others. In this case, it is useful to think of zero-point fluctuations as pairs of virtual particles that appear simultaneously at some point in spacetime, diverge, and then come back together and annihilate. They are called virtual because they cannot be observed directly, but their indirect effects can be measured, and the results of these measurements correspond to theoretical predictions with remarkable accuracy. In the presence of a black hole, one of the pair of particles may fall into the black hole, while the other remains free and escapes to infinity. From the perspective of an observer far from the black hole, the escaping particles are emitted by the black hole. The spectrum of the black hole is exactly the same as what we would expect to see from any heated body with a temperature inversely proportional to the gravitational field at the horizon, that is, at the boundary of the black hole. In other words, the temperature of a black hole depends on its size. A black hole with a mass several times that of the Sun has a temperature of about 1/1,000,000th of a degree above absolute zero, and if the black hole is larger, its temperature is even lower. Thus, any quantum radiation from such black holes is completely overshadowed by the radiation left over from the Big Bang, since its temperature is 2.7 degrees. It might be possible to detect radiation from significantly hotter and smaller black holes, but they seem to be quite rare, which is unfortunate. However, we have indirect evidence suggesting the existence of such radiation. This evidence relates to the early universe. It is believed that at very early stages, the universe underwent a phase of inflationary expansion, during which it experienced a continuously increasing expansion. This period was so rapid that some objects receded from us so far that their light would not reach us, as the universe would expand too much and too quickly during its propagation. In other words, there was an event horizon in the universe, just like in a black hole, separating the region from which light reached us from the region from which it did not. Reasoning suggests that thermal radiation should have originated from this horizon, just like from the event horizon of a black hole. We already know that a source of thermal radiation should have a characteristic spectrum of density fluctuations. In this case, the density fluctuations would have expanded along with the universe. When their scale became larger than the size of the event horizon, they would have frozen, and today we could observe them as small variations in the temperature of the cosmic microwave background radiation left over from the birth of the universe. Indeed, the results of observations of these temperature variations closely match the predicted magnitude of thermal density fluctuations. But even if this observation of black hole radiation is not entirely direct, everyone who has dealt with this issue agrees that radiation must exist. Otherwise, there would be discrepancies with other theories that have been validated by observations. This leads to a significant conclusion from the perspective of determinism. Radiation from a black hole carries away energy, which means that the black hole must lose mass and shrink. This, in turn, means that the temperature of the black hole rises and its radiation increases. Sooner or later, the mass of the black hole will decrease to zero. We do not know how to calculate what will happen at that moment, but it seems logical and natural that the black hole will simply disappear. But what then happens to that part of the wave function inside the black hole and the information about what fell into the black hole that it contains? The first thought that comes to mind when the black hole finally disappears is that this part of the wave function and the information it carries will reappear. However, transferring information comes at a cost, which is obvious, even if it is just a phone bill. Transferring information requires energy, and in the final stages of a black hole's life, there is very little energy left. Thus, information in a black hole has only one reliable way to escape: by gradually disappearing along with the radiation. However, according to the picture in which one particle from a virtual pair falls into the black hole while the other remains free, one cannot expect that the free particles are somehow linked to the fallen one and carry any information about it. Therefore, the only answer is that the information contained in that part of the wave function that ended up in the black hole is lost forever. Such a loss of information significantly impacts determinism. First of all, we noted that even if one knows the wave function, after the black hole disappears, it is impossible to invert the Schrödinger equation and calculate what the wave function was before the black hole formed. This depends on that fragment of the wave function that has vanished into the black hole. We are accustomed to thinking that we know the past with certainty, but if information is lost in black holes, that is not the case. Anything could have happened. However, in general, people, like astrologers and their consultants, are more interested in predicting the future than, so to speak, in post-dicting the past. At first glance, it seems that the loss of part of the wave function in a black hole will not hinder us from predicting what the wave function will be outside the black hole. However, it turns out that this loss does indeed obstruct predictions, which becomes clear when considering the thought experiment proposed by Einstein, Boris Podolsky, and Nathan Rosen in the 30s. Imagine that a radioactive atom decays and emits two particles in opposite directions with opposite spins. An observer who looks at only one particle cannot predict which way it is spinning, right or left. But if they determine that it is spinning right, they can accurately say that the second particle is spinning left, and vice versa. Einstein thought this proved the absurdity of quantum theory, since the second particle could be on the other side of the galaxy by that time, but the observer would instantly know which way it was spinning. Nevertheless, other scientists largely agreed that Einstein was mistaken here. Their quantum theory shows that the thought experiment by Einstein, Podolsky, and Rosen does not demonstrate that information can be transmitted faster than the speed of light. That would be absurd, One cannot conclude that if your particle is spinning right, then the particle of a distant observer is spinning left. In fact, this thought experiment describes precisely what happens with black hole radiation. The pair of virtual particles possesses a wave function that predicts they must have opposite spins. We would like to predict the spin and wave function of the free particle, which we could do if we observed the particle that fell into the black hole. However, now that particle is inside the black hole, and its spins and wave function are unmeasurable there. Therefore, it is impossible to predict either the spin or the wave function of the surviving particle. It may have different spins and different wave functions with varying probabilities, but it does not have its unique spin or wave function. It may seem as if our ability to predict the future is even more curtailed. The classical views of Laplace, which held that one could predict both position and velocity of a particle simultaneously, had to be changed when the uncertainty principle showed that this is not possible. However, the wave function can still be measured, and using the Schrödinger equation, one can predict what it should be in the future. This means one can accurately predict one combination of speed and position, exactly half of what could be known according to Laplace's thinking. We can accurately predict that particles have opposite spins, but if one particle falls into a black hole, we cannot assert anything with certainty about the remaining one. Thus, outside the black hole, there are no measurements that can be determined precisely. Our ability to make specific predictions is reduced to zero. It turns out that astrology predicts the future no worse than the laws of physics. Many physicists were displeased with this curtailment of determinism, and thus they suggested that it is still possible to extract information about what is inside a black hole. For many years, this was merely a passionate hope that some way would be found to preserve information. But in 1996, Andrew Strominger, a manager, and Kamran Vafa made a significant step toward solving this problem. They envisioned a black hole as a construction made up of many components called p-branes. Recall that p-branes can, in particular, be thought of as sheets that move not only through 3 spatial dimensions, but also through 7 additional curled-up dimensions that we do not notice. In some cases, it can be proven that the number of waves on the p-branes equals the amount of information that, according to our calculations, is contained in a black hole. When particles collide with p-branes, they excite additional waves within them. Similarly, if waves moving on p-branes in different directions converge at a certain point, a peak of such magnitude arises that a part of the p-brane detaches and flies away as a particle. It turns out that p-branes can absorb and emit particles, much like black holes. One can conclude that the p-brane theory is an effective theory, meaning that while we do not necessarily have to envision thin sheets moving in flat spacetime and believe in them, black holes can behave as if they are made of such sheets. It is like water. Yes, it consists of billions and billions of H2O molecules interacting in complex ways. But if we imagine it as a homogeneous liquid, it serves as a great effective model. The mathematical model, suggesting that black holes consist of p-branes, yields results similar to those of the previously described hypothesis of virtual particle pairs, meaning that from a positivist perspective, this model is no worse, at least for certain classes of black holes. For these classes, the p-brane model predicts exactly the same radiation rate as the virtual particle pair model, but with one important caveat. In the p-brane model, the information about what falls into the black hole is stored in the wave function of the waves on the p-branes. P-branes are viewed as sheets in flat spacetime, so time will flow smoothly forward, light rays will not bend, and information in the waves will not be lost. Rather, it will eventually emerge from the black hole as radiation. Thus, according to the p-brane model, one can use the Schrödinger equation to calculate what the wave function will be in the future. Nothing will be lost. Time will flow smoothly forward, and we will achieve complete determinism in the quantum sense. Which of these pictures is correct? Does part of the wave function get lost in a black hole, or does the information somehow find a way out, as the p-brane model suggests? This is one of the main questions in modern theoretical physics. Many believe that recent research indicates that information is not lost. The world is predictable and safe, and nothing unexpected can happen. But this is not accurate. If one takes Einstein's general theory of relativity seriously, one must allow for the possibility that space-time is knotted and information is lost in the folds. How can one protect the past? Are time travel possibilities? Can an advanced civilization return to the past and change it? Considering that Stephen Hawking, who lost the previous bet on this matter because he did not demand universality, remains firmly convinced that naked singularities are bad and should be prohibited in the name of the laws of classical physics. And considering that John Preston and Kip Thorne won the previous bet, they still regard naked singularities as objects of quantum gravity that can indeed exist without being covered by event horizons, the entire universe on display. Hawking proposes a kill switch, and Thorne accepts the bet that when any form of classical matter or field that cannot become singular in flat spacetime is combined with general relativity through classical Einstein equations, then the dynamic evolution from general initial conditions, that is, with an open set of initial data, will never lead to naked singularities. It does not extend into past geodesics. The loser is obliged to reward the winner with a veil to cover the nakedness of the victor. The veil should be embroidered with appropriate words indicating complete surrender. Stephen Hawking, John Preston, and Kip Thorne, Pasadena, California, February 5, 1997. Openly discussing time travel is a dangerous business. You risk either incurring public outrage for wasting taxpayers' money. After all, why spend it on such nonsense? Or receiving a notice that your research is classified because it constitutes a military secret. How to defend against an opponent who has a time machine and can change history and seize power over the world. Only a few have the reckless courage to work on such a politically slippery topic. The foundation of all modern debates about time travel is Einstein's general theory of relativity. According to Einstein's equations, space and time are dynamic. These equations describe how matter and energy in the universe warp space and time. Within the framework of general relativity, personal local time measured by wristwatches only increases, just as in Newtonian theory, or in flat spacetime of special relativity. However, now there is a scenario in which spacetime is warped so much that one can embark on a journey in a spaceship and return before one departs. This could happen, in particular, if wormholes exist, tubes of spacetime connecting different regions of space and time. The idea is that if you direct a spaceship into one mouth of a wormhole, it will emerge from the second mouth at a different time and place. Wormholes, if they exist, would theoretically allow one to bypass the speed of light limitation in space. if a ship travels at a speed less than the speed of light, crossing a galaxy would take hundreds of thousands of years according to relativity. But through a wormhole, you could be bored on the other side of the galaxy and make it back in time for lunch. However, it can be proven that if wormholes exist, they could allow one to return before the departure. So in principle, nothing would stop one from, say, blowing up a rocket on the launch pad and preventing oneself from taking off. This is a variation of the grandfather paradox. What happens if you go back in time and kill your grandfather before he has a chance to conceive your father? Of course, this is only a paradox if one assumes that you have the opportunity to return to the past and do whatever you please. We will focus on whether the laws of physics allow for such strong distortions of spacetime that a macroscopic body, like a spaceship, could return to its own past. According to Einstein's theory, a spaceship is forced to move at a speed below the local speed of light, exploring so-called time-like trajectories in spacetime. Therefore, we can rephrase this question in physical terms. Does spacetime allow for closed time-like curves, that is, curves that continuously return to their starting point? We can answer this question on three levels. The first is Einstein's general theory of relativity, which assumes that the universe has a well-defined history without any uncertainty. For this classical theory, we have a fully developed picture. However, as we have already seen, this theory is not entirely correct, as we observe that matter adheres to the uncertainty principle and is subject to quantum fluctuations. Therefore, we can ask the question of time travel at the second level, the level of semi-classical theory. Here, we assume that matter behaves according to quantum theory, the uncertainty principle, and quantum fluctuations. However, spacetime is well defined, and the classical picture is not as complete, yet we have some idea of where to go next. Finally, we are left with a complete quantum theory of gravity, although we still do not know how it works in terms of this theory, where uncertainties and fluctuations affect not only matter, but also spacetime itself. It is even unclear how to formulate the question of the possibility of time travel. Perhaps the most we can do is to ask how inhabitants of regions where spacetime approaches classical and is free from uncertainty should interpret their observations. Will they think that time travel has occurred in regions with strong gravity and significant quantum fluctuations? Let us begin with the classical theory of flat spacetime from the special theory of relativity. The theory of relativity without gravity does not allow for time travel, nor does the curved spacetime studied by Einstein. Therefore, it was a great shock for Einstein when, in 1949, Kurt Gödel, the author of Gödel's theorem, discovered a spacetime representing a universe filled with rotating matter, where time loops pass through every point. The solution went further and required a cosmological constant that may not necessarily exist in nature. However, subsequently, other similar solutions were found that did not require a cosmological constant. The case where two cosmic strings move past each other at high speed is particularly interesting. Cosmic strings are not the same as strings from string theory, although there is some connection between them. These are objects that have length and very small cross-sections. Their existence is predicted by some theories of elementary particles. The spacetime around cosmic strings is flat. However, this flat spacetime has a wedge cut out of it, with the sharp end pressing against the string. It is like a cone. Take a large paper circle, cut out a segment like a slice of pie, a wedge with an angle at the center of the circle. Now throw away the cut-out piece and glue the cut edges of the remaining piece of the circle together, and you will get a cone. This is the model of spacetime in which a cosmic string exists. Note that since the surface of the cone is the same flat sheet of paper you started with, minus the wedge, it can still be called flat, except at the tip. The curvature at the tip is evident, as the circumference described around the tip is smaller than the circumference described at the same distance from the center of the original flat paper circle. In other words, the circumference at the tip is shorter than that of a circle of the same radius in flat space because a segment has been cut out of it. Similarly, in the case of a cosmic string, the wedge removed from flat spacetime shortens the circles around the string, but does not affect either time or distance along the string. This means that the spacetime around a single cosmic string does not contain any time loops, so traveling to the past is impossible there. But if there is a second cosmic string moving relative to the first, then the direction of time on it will be a combination of the direction of time and space on the first, meaning the wedge cut for the second string will shorten both the distance in space and the interval in time from the perspective of an observer moving along with the first string. If cosmic strings move relative to each other at speeds close to the speed of light, the time dilation around both strings may be so significant that a traveler could return before they set out. In other words, there are time loops that could allow travel to the past. The space-time of cosmic strings contains matter with positive energy density and corresponds to the physical laws we know. However, the distortion that creates time loops extends infinitely in space and goes infinitely far back in time. Thus, these spacetimes are inherently endowed with the possibility of time travel. We have no reason to believe that our universe contains such a distortion, and we have no reliable data on visitors from the future. I do not take into account conspiracy theories suggesting that they come from the future and that the government knows about it but is hiding it. The government is not particularly adept at hiding things, as experience shows. Therefore, I assume that in the distant past, there were no time loops. More precisely, in the past of some surface in spacetime, let's call it S, the question is, can any advanced civilization create a time machine? That is, can it modify spacetime in the future so that time loops arise in a limited region of space? I speak of a limited region because even the most advanced civilization is presumably capable of controlling only a limited part of the universe. In science, the correct formulation of the problem often constitutes a lion's share of the solution, and we have a good example of this. Time travel is possible in regions of spacetime where there are time loops, trajectories moving at speeds less than the speed of light, but somehow returning to their starting point in space and time due to the distortion of spacetime. Since I have assumed that there were no time loops in the distant past, there must exist, so to speak, a time travel horizon, a boundary separating the region where time loops exist from the region where they do not. The time travel horizon is very much like the event horizon of black holes. The event horizon of a black hole is formed by light rays that just barely fell into the black hole but managed to escape, while the time travel horizon is formed by light rays that nearly meet themselves. Now, as a criterion for the existence of a time machine, I take the so-called horizon generated in a limited region, that is, a horizon formed by light rays emanating from a limited region. This means they do not originate from infinity or a singularity, but arise in a limited area where time loops exist. That is, precisely in such a region that should have been created by the advanced civilization we are discussing. Even without Einstein's equations, I can show that, in general, a horizon generated in a limited region contains a light ray that meets itself. That is, a light ray that repeatedly returns to the same point. Each time, the light around it will increasingly shift toward the blue end of the spectrum, so the images will become bluer. The peaks of the light pulse waves will get closer together, and the light will return over shorter intervals of its own time. Essentially, a particle of light, according to its own time measurement, will have a limited history, even though it spins in a limited area and does not fall into a singularity. It may seem strange that a particle of light completes its history in a limited time. But I can also prove that there are trajectories moving at speeds less than the speed of light that have only a limited duration. These are likely the histories of observers caught in a closed region before the horizon. They will move in circles faster and faster and eventually reach the speed of light in a finite time. So, if a beautiful alien from a flying saucer lures you into a time machine, be careful, or you might find yourself caught in such a recurring limited duration history. These results do not depend on the specific form of Einstein's equations. They are influenced only by how spacetime must be distorted to create time loops in a limited region. However, we can now ask the following question. What kind of matter must an advanced civilization use to warp spacetime to such an extent that it can build a time machine in a limited area? Perhaps there is positive energy density everywhere, as in the spacetime of cosmic strings I just mentioned. The spacetime of cosmic strings does not meet my requirement for time loops to form in a limited area. However, one might think that it is simply because cosmic strings have infinite length. One could imagine a time machine in a limited area created based on limited loops of cosmic strings with universally positive energy density. It is unfortunate to disappoint people like Kip, who long to travel to the past, but with universally positive energy density, this is impossible. I can prove that negative energy is needed to create a time machine in a limited area. Energy density in classical theories is always positive, so time machines in limited areas are excluded at this level. But in semi-classical theory, where it is assumed that matter behaves according to quantum theory, while space behaves classically in certain respects, everything is quite different. As we have seen, the uncertainty principle of quantum theory means that fields are always unstable and fluctuate up and down, even in seemingly empty space, and then possess infinite energy density. Thus, to obtain the finite energy density observed in the universe, one must subtract an infinite number. After such subtraction, the energy density can indeed become negative, at least locally. Even in flat space, one can find a quantum state where the energy density is locally negative, although the total energy is positive. The listener may wonder if all these negative quantities indeed cause spacetime to warp in such a way as to build a time machine in a limited area. However, it seems that this is indeed the case. Otherwise, it would not be possible. Quantum fluctuations mean that even seemingly empty space is full of pairs of virtual particles that arise together, disperse, and then meet again and annihilate. One of the pair of virtual particles always has positive energy, while the other has negative energy. If there is a black hole nearby, and a particle with negative energy falls into it, the particle with positive energy escapes to infinity and appears there as radiation, carrying positive energy away from the black hole. The particle with negative energy that falls into the black hole causes it to lose mass and slowly evaporate, while its horizon shrinks in size. Ordinary matter with positive energy density has gravitational attraction and distorts spacetime in such a way that light rays bend toward each other, similar to how a ball on a rubber sheet from Chapter 2 always causes smaller balls to converge toward it and prevents them from rolling away. From this, it follows that the area of a black hole's horizon can only increase over time, not decrease. For the horizon of a black hole to shrink, the energy density on the horizon must be negative, distorting spacetime in such a way that light rays diverge. The evaporation of black holes shows that at the quantum level, energy density can sometimes be negative and distort spacetime in the direction necessary for creating a time machine. Thus, one can imagine an advanced civilization capable of arranging everything so that negative energy density is sufficient to create a time machine that could transport macroscopic bodies, say, spaceships. However, there is a significant difference between the horizon of a black hole formed by light rays that continue on their way and the horizon of a time machine within which closed light rays are trapped, spinning in place and constantly returning to their starting point. A virtual particle moving along such a closed trajectory will constantly return the energy of its ground state to the starting point. So one can expect that at the horizon, that is, at the boundary of the time machine, the region where one can travel to the past, the energy density will be infinite. This directly follows from calculations in cases where the conditions are simple enough to perform precise computations. Therefore, a person or spacecraft attempting to cross the horizon and enter the time machine will have to deal with powerful radiation. Thus, future time travel promises grim prospects, or rather, blinding white radiation. The energy density of matter depends on its state, so it may be that an advanced civilization can make the energy density at the boundary of the time machine finite by freezing or removing the virtual particles running around in the closed time loop. However, it is unclear whether such a time machine would be stable, as even the slightest disturbances, for example, if someone crosses the horizon to enter the time machine, would cause circulating virtual particles to reappear, and thunder would strike. It would be wonderful if scientists could freely discuss this issue without risking becoming targets of contempt and ridicule. Even if it turns out that time travel is impossible, it is important to understand why this is the case. To provide a definitive answer to this question, let us consider quantum fluctuations not only in material fields, but also in spacetime itself. This is likely to cause some blurriness in the trajectories of light rays and the entire concept of controlling time. Indeed, one can consider that radiation from black holes escapes because there are quantum fluctuations in spacetime, and therefore the horizon is definitely fuzzy, since we do not yet have a complete theory of quantum gravity, making it difficult to say when you should expect the effects and fluctuations of spacetime. Nevertheless, we can hope to gain some insights from the sum of histories in Feynman's framework, as discussed in Chapter 3. Each history represents a warped spacetime containing material fields within it. Since we need to sum all possible histories, they are only those that satisfy certain equations and the sum must include spacetimes whose distortions are so strong that they allow for time travel to the past. Therefore, the question arises, why do time travels not occur everywhere? The answer is that time travel does indeed happen on a microscopic scale. We simply do not notice it. If we apply the idea of the sum of histories to particles, we must include in this sum those histories where particles move faster than the speed of light, and those where they return to the past. In particular, we need to consider histories in which particles run along closed loops in space and time. This is like in the movie Groundhog Day, where the journalist hero has to live the same day over and over again. It is impossible to observe particles with such closed histories directly using a detector. However, indirect effects have been measured in numerous experiments. For example, small changes in the wavelength of light emitted by hydrogen atoms have been measured. This change was caused by electrons moving along closed loops. A small force has also been registered between parallel metal plates. This force was caused by the fact that the histories with closed loops placed between the plates are slightly fewer than in the area outside the plates. This is one of the equivalent interpretations of the Casimir effect. Thus, the existence of closed histories has been experimentally proven. One might argue whether closed histories of particles have any relation to the curvature of spacetime, as they arise even in space of fixed curvature, particularly in flat space. However, in recent years, we have discovered that physical phenomena can often be described in two equally valid ways. One can equally well say that a particle moves along a closed loop in a given fixed space, and that the particle remains stationary while space-time around it fluctuates. The question is only which sum you are calculating. First, the sum over particle trajectories, or the sum over warped spacetimes. Therefore, it seems that quantum theory allows for time travel on a microscopic scale. This is of no use for science fiction. You cannot travel to the past and kill your grandfather. Therefore, it is worth asking the question, can the total probability of histories take on significant value in the vicinity of spacetimes with macroscopic time loops? To investigate this question, it makes sense to study the sum of histories of material fields in several background spacetimes that progressively approach conditions allowing for time loops. It would seem that at the moment of the first appearance of a time loop, something spectacular should happen. The background spacetime of the type we studied is closely related to the so-called Einstein universe, a model of spacetime proposed by Einstein during the years when he thought that the universe was static and did not change over time, neither expanding nor contracting. In the Einstein universe, time flows from an infinite past to an infinite future, but the spatial directions in it are finite and closed, looping back on themselves, like the surface of the Earth, just with one additional dimension. This spacetime can be imagined as a cylinder with a long axis directed in time and a cross-section representing three spatial dimensions. The Einstein universe does not expand, so this is not the universe we live in. Nevertheless, in such a spacetime, it is convenient to study questions of time travel, as this model is very simple and makes it easy to compute sums of histories. Let us briefly divert from time travel and consider matter in the Einstein universe, rotating around some axis. If you are on the axis, you remain in the same point in space, as if at the center of a carousel in a playground. But if you are not on the axis, you will move in space while rotating around the axis. The farther you are from the axis, the faster you move. This means that if the universe were infinitely spatial, points at a sufficiently large distance from the axis would rotate at speeds exceeding that of light. However, since the spatial directions of the Einstein universe are finite, there exists a critical distance below which the universe will not have regions rotating at speeds exceeding the speed of light. Now consider the sum of histories of particles in the rotating Einstein universe. If the rotation is slow, and a particle with a given amount of energy can take multiple trajectories, then the sum of all histories of the particle under these conditions provides a wide range of possibilities. This means that the probability in such conditions in the sum of all histories of warped spacetimes will be high, meaning this history will be among the more likely ones. However, as the rotation rate of the Einstein universe approaches the critical value, when the speed of motion at the outer edge approaches the speed of light, classical laws will allow only one trajectory for the particle at the edge, namely, motion at the speed of light. This means that the sum of all histories of the particle will be low. Therefore, the probability of such conditions in the sum of all histories of warped spacetime will be low, meaning they will be among the least likely. But what relation does the Einstein universe have to time travel and time loops? The point is that they are mathematically equivalent to other conditions where time loops are allowed. I mean a universe that expands in two spatial dimensions, but does not expand in the third. It is periodic, meaning that if you travel a certain distance in that direction, you will return to the starting point. However, each time you make a loop in the third spatial dimension, your speed in the first or second dimension increases. If the increase is small, there are no time loops. However, consider a sequence of conditions with increasing speed increments. At a certain critical increment, time loops will appear. It is no surprise that the critical increment corresponds to the critical rotation speed in the Einstein universe, as the calculations of the sum of histories in these models are mathematically equivalent. It follows that the probability of such conditions approaches zero as the distortion necessary for time loops approaches. In other words, the probability of achieving the distortion of spacetime necessary to create a time machine is zero. Star Trek is so popular because it presents a cozy and comforting picture of the future. In Star Trek, a society far ahead of ours in science, technology, and political organization is depicted. The latter, however, is not difficult to ascertain, as great historical changes have occurred over time with inevitable periods of hardship and distress. However, we are shown an era when science, technology, and political organization have practically reached perfection. I want to question this picture and ask, will we ever reach the final stage of scientific and technological progress? Stability. Over the last 10,000 years or so, since the last ice age, humanity has never been in a state where the sum of knowledge was constant and technology did not evolve. There have been several setbacks, for example, in the Middle Ages after the fall of the Roman Empire. However, the planet's population, which serves as a criterion for our technological ability to sustain life and feed ourselves, has been steadily increasing, except for individual setbacks, including the Black Death. Over the last 200 years, the population has been growing exponentially, meaning by the same percentage each year. Currently, the population growth rate is 1.9% per year. It may not seem like much, but it implies that the planet's population doubles every 40 years. There are other criteria for technological development. In recent decades, this includes electricity consumption and the number of scientific papers. They also show exponential growth with a doubling period of less than 40 years. There are no signs that the scientific and technological process will slow down and stop in the near future, and this certainly will not happen by the time of Star Trek, which takes place in a relatively near future. But if population growth and electricity consumption continue at the current pace, by the year 2600, the entire population of the planet will be shoulder to shoulder from consuming electricity, and the Earth will glow red hot. If we were to line up all the new books being published, one would have to move at a speed of 140 kilometers per hour to keep from losing sight of the end of the line. Naturally, by the year 2600, new literary works and scientific papers will likely exist more in electronic form than as printed books and journals. In any case, if their number continues to grow exponentially, 10 articles will be published every second. There will be no chance of reading them all. Clearly, the current exponential growth cannot continue forever. What will happen? One possibility is that we will self-destruct as a result of some anthropogenic catastrophe, such as a nuclear war. A common grim joke states that we have not yet made contact with aliens because any civilization that reaches our level of development loses stability and self-destructs. However, I am an optimist. I do not believe that the human race has come this far only to blow itself up just when things are getting interesting. It is possible that the picture of the future painted in Star Trek, where we have reached a very high level of scientific and technological development, is accurate, but we have plateaued. It may be true regarding our knowledge of the fundamental laws governing the universe. Perhaps there is a grand theory of everything, and we will discover it in the not-so-distant future. If this theory exists, it will allow us to determine whether we can realize the dream of Star Trek regarding engines that work by warping space-time. According to current understanding, we will have to explore our galaxy slowly and tediously on starships that travel slower than light. But since we do not yet have a theory of everything, we cannot rule out the possibility that we will be able to create a warp drive. On the other hand, we already know the laws that apply almost all the time, except in the most extreme situations. The laws that govern the crew of the Enterprise, if not the ship itself. However, similarly, we will never reach a plateau in how we apply these laws, nor in the complexity of the systems we can create with their help. The most complex system we deal with, by far, is undoubtedly our organism. Apparently, life originated in the primordial oceans that covered the Earth 4 billion years ago. We do not know how this happened. It is likely that a random collision of atoms led to the emergence of macromolecules capable of self-replication and self-organization into more complex structures. However, we do know that about 3.5 billion years ago, the most complex molecule, DNA, emerged. DNA is the foundation of all life on Earth. It has a double helical structure, resembling a spiral staircase. It was discovered by Francis Crick and James Watson in the Cavendish Laboratory in Cambridge in 1953. The two strands of the double helix are connected by pairs of bases, like steps. There are 4 bases in DNA: adenine, guanine, thymine, and cytosine. The order in which they appear in the spiral carries genetic information that allows DNA to build a living organism and replicate itself. When DNA copies itself, it sometimes makes mistakes in the proportions or order of the bases in the spiral. In most cases, copying errors deprive DNA of its ability to replicate or significantly reduce it, and thus such genetic errors, also known as mutations, die out. However, in some cases, a mutation error increases DNA's chances of survival and reproduction. Such changes become entrenched in the genetic code, allowing the information contained in the DNA sequence to gradually evolve and become more complex. Since biological evolution is largely a random wandering through the space of all genetic possibilities, it has progressed very slowly. The complexity or amount of information bits encoded in DNA is roughly equal to the number of bases in the molecule. For the first 2 billion years, the increase in complexity seems to have been 1 bit of information every 100 years. The increase in DNA complexity gradually accelerated and reached 1 bit per year in the last few million years. But then, approximately 6,000 to 8,000 years ago, a significant leap occurred. We invented written language. This meant that information could be passed from generation to generation without waiting for the results of the very slow process of random mutations and natural selection. Complexity skyrocketed. A single paperback novel contains as much information as the difference in DNA between humans and monkeys, and 30 tons of encyclopedias can contain the code for the entire sequence of human DNA. Most importantly, information in books can be quickly changed and supplemented. Currently, human DNA is changing at a rate of about 1 bit per year through biological evolution, but every year, 200,000 new books are published, meaning new information arrives at a rate of over 1 million bits per second. Most of this information, of course, is pure junk. But even if it contains 1 useful bit per million, the growth rate is still 100,000 times faster than biological evolution. The transmission of data through external, non-biological means has led humanity to dominate the planet, and our population is growing exponentially. But now, we find ourselves on the brink of a new era, where we will be able to increase the complexity of our internal DNA archive without waiting for the slow process of biological evolution to do so. Over the last 10,000 years, human DNA has not changed much, but we will likely be able to completely restructure it in the coming millennia. Of course, many believe that genetic modification of humans should be banned. However, it is unlikely that we will be able to prevent work in this area. Large-scale genetic modification of plants and animals will be permitted for economic reasons, and someone will undoubtedly try to do the same with humans. If totalitarianism does not establish itself worldwide, someone somewhere will create an enhanced human. It is clear that the creation of an enhanced human will give rise to enormous socio-political problems. I by no means advocate for the genetic modification of humans, nor do I consider it desirable. I simply want to say that it will happen regardless of our desires. This is why I do not believe in science fiction, like Star Trek, where humans in 400 years are no different from us. I think humanity as a species and its DNA will rapidly become more complex. We should acknowledge that this is quite likely and think about how we will deal with it. In some sense, humanity needs to improve its mental and physical qualities, as it will have to survive in an increasingly complex world and tackle new challenges, including space travel. Furthermore, Humans must evolve as biological systems to avoid being outpaced by electronic systems. Currently, computers are much faster than us, but they show no signs of intelligence, which is not surprising, as modern computers are simpler than the brain of an earthworm, which is not known for its remarkable intellectual achievements. However, computers adhere to what is known as Moore's law. Their speed and complexity double every 18 months. We face exponential growth again, which cannot continue indefinitely, but it will likely persist until the complexity of computers matches that of the human brain. Some say that computers will never possess true intelligence. However, it is unclear what true intelligence actually is. Nevertheless, it seems to me that if very complex chemical molecules in the human body can react in such a way that a person becomes intelligent, then no less complex electronic circuits can also make a computer behave intelligently. And if computers become intelligent, it is possible that they will create even more complex and intelligent computers themselves. But will this growth of biological and electronic complexity continue indefinitely, or does it have a natural limit? From a biological perspective, the limit of human intelligence is currently determined by the size of the brain, that is, the skull capable of passing through the birth canal. However, I believe that it will not be long before we learn to grow infants outside of the human body, thus removing this limitation. Sooner or later, however, increasing the size of the human brain through genetic engineering will face a new obstacle. The chemical substances that transmit signals regulating our mental activity act relatively slowly, meaning that any further increase in the complexity of the brain will come at the cost of speed. One can be very intelligent or think quickly, but not both at the same time. Still, I believe we will be able to become much smarter than most characters in Star Trek. This is not difficult. Electronic circuits face the same problem of complexity and speed as the human brain. However, in this case, the signals are electrical rather than chemical, which means they are transmitted at the speed of light, which is much faster. On the other hand, the speed of light already serves as a practical limitation in the creation of fast computers. The situation can be improved by making the circuits smaller, but ultimately, their creators will face a barrier in the atomic nature of matter. However, there is still some room for action before that barrier. Moreover, electronic circuits have a way to increase their complexity while maintaining speed. They need to copy themselves into the human brain. No single processor in the brain processes each command sequentially. It has millions of processors that work simultaneously. Such massive parallel data processing is the future not only of human intelligence, but also of electronic intelligence. If we assume that we do not destroy ourselves in the next 100 years, we will likely first spread out across the planets of the solar system, and then to neighboring stars. But it will not be like in Star Trek or Babylon 5, where almost every planetary system discovers a new race very similar to humans. Humanity has existed in its current form for only about 2 million years out of approximately 15 since the Big Bang. So even if there is life in other planetary systems, the chances of encountering it at a familiar human stage are extremely low. Most likely, any extraterrestrial life we encounter will be either much more primitive than ours or much more advanced. If it is highly developed, why have representatives of other civilizations not crossed the galaxy and visited Earth? If aliens had been here, they would have undoubtedly left traces. It is much more reminiscent of Independence Day than of extraterrestrial visitors. How can we explain the fact that extraterrestrial guests are not in a hurry to visit us? It is possible that there exists a highly developed civilization somewhere that knows about us, but prefers to leave us to stew in our own primitive broth. However, it is doubtful that extraterrestrials would treat lower forms of life so delicately. We, for instance, do not feel very sorry for the insects and worms we crush with every step. A more plausible version is that the probability of life arising on other planets or the development of intelligent life is very low. Since we claim to be rational, perhaps without much basis, we tend to believe that intelligence is an inevitable consequence of evolution. But this is not necessarily the case. It is unknown whether intelligence provides an advantage in natural selection. Bacteria manage perfectly well without intelligence and will outlive us if our so-called intelligence leads us to self-destruction through nuclear war. Therefore, in exploring the galaxy, we will likely find primitive forms of life, but we will hardly encounter beings similar to ourselves. The future of science does not resemble the benevolent picture painted in Star Trek. We do not await a universe populated by many humanoid races with advanced but essentially static science and technology. No, most likely we will not be alone, but the complexity of our biological and electronic systems will be rapidly increasing. However, this is unlikely to happen in the next 100 years, and that is all we can assert with certainty. But by the end of the next millennium, if we survive to that time, our lives will be fundamentally different from Star Trek. What will the path of our discoveries look like? Will the search for a complete theory of everything that governs the universe and everything in it lead to success? Perhaps we have already discovered the theory of everything. It is M theory. As far as we know, it does not yet have unified formulations. Instead, we have found a whole set of different, seemingly unrelated theories that are approximations of the same fundamental theory in different limiting cases. For instance, Newtonian theory of universal gravitation is an approximation of Einstein's theory of relativity in the limiting case of weak gravitational fields. M theory is like a puzzle. It is easiest to find and place the pieces at the edges. At the boundaries of M theory, where certain quantities are small, we have a fairly good understanding of these edges. But in the center of the M theory puzzle, there is still a gap, and we do not know what is happening there. Until we fill this gap, we cannot claim to have discovered the theory of everything. What lies in the center of M theory? Will we discover dragons or something equally astonishing, as on ancient maps of uncharted lands? Accumulated experience shows that each time we move to observations at smaller scales, we usually find unexpectedly new phenomena. In the early 20th century, we understood how nature operates at the scales of classical physics, which perfectly explains everything from the distance between stars to about 1/100th of a millimeter. According to classical physics, matter is a continuous medium with properties such as viscosity and elasticity. However, over time, evidence emerged that matter is not homogeneous but granular. It consists of tiny constituent parts called atoms. The word atom is of ancient Greek origin and means indivisible. However, it soon became clear that atoms themselves consist of electrons that orbit a nucleus made up of protons and neutrons. Achievements in atomic physics in the first 30 years of the 20th century allowed us to advance down to 1/1,000,000th of a millimeter, and we discovered that protons and neutrons consist of even smaller particles, known as quarks. Recent research in nuclear physics and high-energy physics has shown us what happens at scales a billion times smaller. It seems that this could continue indefinitely. We will keep discovering structures at smaller and smaller scales. However, this sequence has a limit, much like a set of Russian nesting dolls that eventually comes to an end. Ultimately, you reach the last, smallest doll, which can no longer be divided. Physicists refer to the smallest doll as the Planck length. To reach even shorter distances, particles with such high energies are required that they can only exist inside black holes. We do not know exactly what the value of the fundamental Planck length will be in M-theory, but it is likely to be just 1 millimeter divided by 100,000 billion. We will never be able to build accelerators capable of exploring such small scales. They would need to be larger than the solar system. So, given the current economic situation, governments are unlikely to fund such a project. However, some recent data gives us hope that it may be somewhat easier and cheaper to discover at least some dragons of M-theory. As discussed in chapters 2 and 3, the set of mathematical models that make up the theory has 10 or 11 dimensions of spacetime. Until recently, it was believed that 6 or 7 additional dimensions were compacted and very small, like a human hair. If you look at a hair under a magnifying glass, you will see that it has thickness, but to the naked eye, it appears as a line with only length as a dimension. Perhaps spacetime is structured similarly. At human, atomic, and even nuclear scales, it appears four-dimensional and almost flat. On the other hand, if you look at very small scales using extremely high-energy particles, you will see that spacetime has 10 or 11 dimensions. And if all additional dimensions are very small, observing them will be very difficult. However, a recent hypothesis suggests that some additional dimensions are likely quite large or even infinite. From the perspective of positivists like me, this hypothesis has a significant advantage. It can be tested at next-generation accelerators or through highly precise measurements of gravitational forces at small distances. Such observations would either disprove this hypothesis or experimentally confirm the existence of other dimensions. Large additional dimensions are a very interesting finding on the path to discovering the ultimate model or theory of everything. If they exist, we live in a brain world, and on the four-dimensional surface of the brain, space-time has even more dimensions. In the brain, matter and non-gravitational forces, such as electricity, are concentrated. Thus, everything that has nothing to do with gravity behaves as if there are only 4 dimensions. In particular, the electric interaction between the nucleus of an atom and the electrons orbiting it weakens with distance precisely at a rate that keeps atoms stable and prevents electrons from falling into the nucleus. All of this would correspond to the Anthropic Principle, which states that the universe must create all conditions for intelligent life. If atoms were not stable, we would not exist, and there would be no one to observe the universe and ask why it appears four-dimensional. On the other hand, gravity, in the form of curvature, permeates all multidimensional spacetime. This means that within this model, gravity behaves differently than the other forces we encounter, as it propagates into additional dimensions and thus weakens with distance faster than one might expect. If this phenomenon of gravity weakening with distance at an accelerated rate were observed at distances accessible to modern astronomy, we would notice its influence on the orbits of planets. These orbits would simply not be stable, as mentioned in Chapter 3. Planets would either fall into the sun or drift off into the cold and darkness of interstellar space. However, this will not happen if the additional dimensions end at another brane located near the branes where we live. When the distance exceeds that between these branes, gravity cannot propagate freely and will essentially be confined within one brane, weakening with distance just enough to ensure the stability of planetary orbits, much like electric forces. On the other hand, if the distance is less than that between the branes, gravity may change more rapidly. Very small gravitational forces between massive bodies have been accurately measured in the laboratory. However, experiments have not yet revealed the influence of branes separated by less than a few millimeters. New measurements are currently being conducted at even shorter distances. In this brane world, we may live on one brane, but there is likely another shadow brane nearby. Since light confined to the brane does not propagate in the space between them, we do not see this shadow world, but we feel the gravitational influence of matter from the shadow brane. From the perspective of an observer on our brane, it seems as if these gravitational forces originate from something truly dark, in the sense that the only way to detect it is to register its gravity. Indeed, to explain why stars rotate around the center of our galaxy at the speed they do, it is necessary to assume that there is more mass there than can be accounted for by all the matter we observe combined. Perhaps the missing mass is provided by exotic types of particles from our world, such as WIMPs, weakly interacting massive particles, or axions, very light elementary particles. However, it is also possible that the missing mass is evidence of the existence of a shadow world containing matter. There may even be shadow people there, bewildered as to why their world lacks the mass necessary to ensure the rotation of their shadow stars around the center of their shadow galaxy. But there is another possibility. In addition to the idea that the additional dimensions end at two branes, they may be infinite but highly curved, like a saddle. Lisa Randall and Roman Sundram have shown that such curvature can play the same role as two branes. The gravitational influence of an object on the brane is limited to the immediate vicinity of the brane and does not propagate infinitely into additional dimensions. Like in the shadow brane model, the gravitational field weakens with distance at precisely the rate that explains both the stability of planetary orbits and laboratory measurements of gravitational forces. However, at close distances, gravity will change more rapidly. Nevertheless, the Randall-Sundram model has a significant difference from the shadow brane model. Bodies moving under the influence of gravity generate gravitational waves, ripples in curvature that propagate through spacetime at the speed of light. Gravitational waves, like light waves, carry energy, and this hypothesis has been confirmed by observations of the binary pulsar PSR 1913+16. If we indeed live on a brane in a spacetime with additional dimensions, the gravitational waves generated by the motion of bodies on the brane would also propagate into other dimensions. If there are two shadow branes, gravitational waves should reflect back and become trapped between these two branes. On the other hand, if there is only one brane, and the additional dimensions extend into infinity, according to the Randall-Sundram model, gravitational waves can leave our world brane forever and carry energy away from it. This would seem to violate one of the fundamental principles of physics, the law of conservation of energy. The total amount of energy is always constant. However, it seems that the law is violated only from our perspective, as we are confined to our brain. Any angel capable of seeing other dimensions would know that the total energy remains the same. It simply spreads out in space. Gravitational waves emitted by two stars orbiting each other should have wavelengths much greater than the radius of the saddle-like curvature of the additional dimensions. This means they are concentrated near the brain and, like gravitational force, essentially cannot propagate into other dimensions without carrying energy away from the brain. However, on the other hand, if gravitational waves are shorter than the curvature of the additional dimensions, they can easily escape from the vicinity of the brain. Significant sources of short gravitational waves can only be black holes. A black hole on the brain propagates both in additional dimensions. If a black hole is small, its shape approaches a spherical one, meaning it spreads into additional dimensions at a distance approximately equal to its size on the brain. On the other hand, a large black hole on the brain spreads out as a black hole confined to the vicinity of the brain. Its thickness in additional dimensions is much less than its width on the brain. As discussed in Chapter 4, quantum theory suggests that black holes are not entirely black. They emit various particles and radiation, like a heated body. Particles and radiation, such as light, will spread across the brain since matter and non-gravitational forces, like electricity, are confined within it. However, black holes also emit gravitational waves. Gravity, unconstrained on the brain, spreads into additional dimensions. If a black hole is large and resembles a pancake, the gravitational waves will remain near the brain, and the black hole will lose energy and consequently mass according to EMC2, at a rate one would expect from a black hole in four-dimensional spacetime. Therefore, the black hole will slowly evaporate and shrink in size until it becomes smaller than the radius of the curvature of the visible additional dimensions. At that moment, the gravitational waves emitted by the black hole will begin to propagate freely into additional dimensions, and observers on the brain will see the black hole or dark star, as Mitchell puts it, as an object emitting dark radiation, radiation that cannot be directly observed on the brain. However, it exists because the black hole is losing mass. This implies that when the black hole completely evaporates, the last burst of radiation from it will appear weaker than it actually is. Perhaps this is why we have not yet observed gamma-ray bursts that could be attributed to dying black holes. However, there is another, more mundane explanation. The universe is still young, and there are not many black holes with such small masses that they are ready to evaporate. Radiation from black holes in the brain world is explained by quantum fluctuations of particles on the brain. However, brains, like everything else in the universe, are also subject to quantum fluctuations. Due to these fluctuations, brains sometimes spontaneously arise and disappear. The quantum emergence of a brain likely resembles the formation of bubbles in boiling water. Liquid water consists of billions of H2O molecules held together by bonds with their nearest neighbors. When the water heats up, the molecules move faster and bounce off one another. Sometimes, when colliding, molecules gain such high speeds that they break bonds in groups and form a bubble of steam surrounded by water. The bubble then either grows or shrinks randomly, with new molecules either joining the steam, or, conversely, most small steam bubbles turning back into liquid. However, some will manage to grow to a certain critical size, after which the bubbles will almost certainly continue to grow. It is these large bubbles that we observe when boiling water. The brain world should behave similarly. According to the uncertainty principle, world brains can emerge from nothing in the form of bubbles, where the brain is the surface of the bubble, and its interior is the space of additional dimensions. Very small bubbles collapse and disappear, but if a bubble reaches a certain critical size due to quantum fluctuations, it is likely to continue growing. People like us, living on the brain and the surfaces of bubbles, believe that the universe is expanding. It is like drawing galaxies on a balloon and then inflating it. The galaxies will drift apart, but none can be considered the center of expansion. We can only hope that no one will find a cosmic pin capable of popping our bubble. According to the hypothesis of no boundaries, the spontaneous emergence of the brain world should have a history in imaginary time resembling a nut, meaning it represents a four-dimensional sphere, like the surface of the Earth, but with two additional dimensions. A four-dimensional sphere cannot be anyone's boundary. The remaining 6 or 7 dimensions of spacetime mentioned in M theory will be compacted to sizes even smaller than a nutshell. However, according to the brain world model, the nut is filled, and the history of the brain we inhabit in imaginary time represents a four-dimensional sphere that serves as the boundary of a 5-dimensional bubble, with the remaining 5 or 6 dimensions compacted and very small. The history of brains in imaginary time defines their history in real time. The most likely history of the bubble in imaginary time is that of a perfectly smooth shell. However, this would correspond to a brain that expands infinitely in real time. According to the inflationary model, no galaxies would form on such a brain, meaning intelligent life would not arise. On the other hand, somewhat less smooth and round histories in imaginary time are slightly less likely, but they correspond to a scenario in real time where the brain first undergoes a phase of inflationary expansion with acceleration and then slows down. As a result of this expansion, followed by deceleration, galaxies could form, and intelligent life could emerge. Einstein's general theory of relativity gives time a shape. How can this be reconciled with quantum theory? What is time? A continuous flow that carries all dreams into the past as sung in old songs, or something like a railway, perhaps with loops and branches. Then one can move forward, but also end up back at a previously visited station on the same branch. The English poet Charles, who lived in the 19th century, wrote, "For me, there is nothing more mysterious than space and time. However, space and time will forget me the least, for I never think about them." We constantly forget about space and time, whatever that means, but sometimes we still ask ourselves, what is time? Where did it begin? And where is it leading us? It seems to me that any viable scientific theory, not necessarily a theory of time, must be based on the principles of the most reliable and constructive philosophy of science, the positivist approach of Karl Popper and other philosophers. According to their worldview, a scientific theory is a mathematical model that describes and codifies the observations we make. A good theory explains a wide range of phenomena using a few simple postulates and makes specific predictions that can be tested. If the predictions align with observations, the theory passes the test. However, it is impossible to prove that it is correct. On the other hand, if observations do not match predictions, one must either abandon the theory or modify it. At least, this is how it should work in practice. Theorists often doubt the accuracy of observations and, moreover, the reliability and moral ethical qualities of the observers. If such a stance is not maintained, the positivist approach cannot even tell what time it is. One can only present some mathematical model of time that scientists consider very good and state what predictions it makes. The first mathematical model of space and time was proposed by Isaac Newton in his work Mathematical Principles of Natural Philosophy, published in 1687. Newton held the chair of Lucasian Professor of Mathematics at Cambridge. According to Newton's model, time and space serve merely as a backdrop for the events that occur, which do not affect them in any way. Time is independent of space and is considered a single line, a railway track, infinitely extending in both directions. Time itself is eternal in the sense that it has always been and always will be. Most of Newton's contemporaries believed, on the contrary, that the physical universe was created more or less in its current state only a few thousand years ago. This discrepancy troubled many philosophers, including the German thinker Immanuel Kant. If the universe was indeed created, why wait endlessly before creating it? On the other hand, if the universe has always existed, why has everything that was supposed to happen not happened yet? Why has history not come to an end? In particular, why has thermal equilibrium not been reached in the universe, meaning all objects have not become the same temperature? Kant called this problem the antinomy of pure reason because he saw a logical contradiction that could not be resolved. However, such a contradiction only arises within the framework of Newton's mathematical model, which posits that time is an infinite line independent of what occurs in the universe. In the years following the publication of Einstein's article, we have adorned his theory with various ribbons and flourishes, but our model of spacetime is still based on what Einstein proposed. How have our ideas evolved since the release of Einstein's revolutionary article? This is the success story of many scientists. Einstein's general theory of relativity adds to the three spatial dimensions to create what is known as spacetime. This theory describes the effect of gravity. The distribution of matter and energy in the universe distorts and curves spacetime, which consequently is not flat. Objects in such spacetime tend to move in a straight line, but since spacetime is curved, their trajectories turn out to be bent, and they move as if influenced by a gravitational field. Let's resort to a crude analogy. Do not take it literally. Imagine a rubber sheet. Now place a large ball on the sheet. This will represent the sun. Under the weight of the ball, the sheet will bend and curve around the sun. If you then roll small balls, like marbles, across the sheet, they will not roll straight across, but will spiral around the heavy object, just like planets around the sun. This analogy is incomplete because it only curves a two-dimensional part of space, the surface of the rubber sheet, while time remains untouched, as in Newton's theory. However, according to the general theory of relativity, which is supported by numerous experiments, time and space are inseparably linked. It is impossible to curve space without affecting time. Thus, time has a shape. By curving space and time, the general theory of relativity transforms them from a passive backdrop on which events unfold into active, dynamic participants in the proceedings. Regarding Newton's theory, where time existed independently of everything else, it would be reasonable to ask, what was God doing before creating the universe? According to St. Augustine, this is not a matter for jokes, like creating from those who dig too deep. This is a serious question that has served as a subject of contemplation for many centuries. According to St. Augustine, before creating heaven and earth, the Lord did nothing. Essentially, this is very close to modern ideas. On the other hand, according to the general theory of relativity, time and space depend on each other and on the universe in which they exist. They are defined based on measurements of certain parameters of the universe, such as the number of oscillations in a quartz clock crystal or the length of a ruler. It is easy to imagine that with such a definition of time within the universe, it must have a minimum or maximum value, meaning a beginning or an end. Asking what was before the beginning or after the end is meaningless, as it lies outside the definition of time. It is evident that understanding whether the mathematical model of general relativity predicts the beginning or end of the universe and time itself was important. Theoretical physicists, including Einstein himself, operated under the belief that time stretches infinitely in both directions. Otherwise, uncomfortable questions about the creation of the universe would arise, seemingly beyond the scope of science. Solutions to Einstein's equations were known that suggested time has a beginning or an end, but these were limited to very specific cases that required numerous symmetries. It was believed that in a real material body collapsing under its own gravity, pressure, or lateral velocities would prevent all matter from collapsing into a single point of infinite density. Similarly, if we trace the expansion of the universe backward in time, matter in the universe should not have originated from a point of infinite density. Such a point came to be known as a singularity, and it could potentially be the beginning or end of time. In 1963, two Soviet scientists, Evgeny Lifshitz and Isaac Kalatnikov, claimed to have proven that the solution to Einstein's equations with a singularity requires a special relationship between matter and velocities. The probability that a solution describing the universe satisfies such a relationship was nearly zero. Almost all solutions that could describe the universe allowed for the avoidance of a singularity of infinite density. Before the era of cosmic expansion, there must have been a phase of contraction during which matter condensed but did not compress infinitely, and then began to spread out again, which would mark the beginning of the current phase of expansion. In this case, time would stretch infinitely from an infinite past to an infinite future. However, Lifshitz and Kalatnikov's arguments did not convince everyone. Within the framework of general relativity, space-time is curved not only by massive bodies, but also by the energy contained within it. Energy is always positive, thus imparting curvature to space-time, causing the trajectories of light rays to bend towards each other. Now let's consider the light cone directed backward in time, formed in space-time by the trajectories of light rays from distant galaxies that reach us at this moment. In a coordinate system where time is plotted on the vertical axis and space on the horizontal, this cone has its apex at the point where we are located. As we move backward in time from the apex to the base of the cone, we observe how galaxies looked earlier and earlier as the universe expands, and at one time, all objects within it were much closer to each other. By looking into the past, we are peering into regions where matter had a higher density. We also notice the faint cosmic microwave background radiation that reaches us through the light cone from earlier times when the universe was much denser and hotter than it is now. If we tune receivers to different frequencies of microwave radiation, we can measure its spectrum, the power distribution across frequencies, and see that this spectrum is characteristic of radiation from a body at a temperature of 2.7 degrees above absolute zero. This radiation won't reheat a pizza, but since its spectrum closely matches the model of radiation from a body at 2.7 degrees, it indicates that the radiation came from regions of space that are opaque to microwaves. Thus, we can conclude that our light cone directed backward in time must have passed through some amount of matter. This matter is sufficient to curve spacetime, so the light rays in our past light cone bend and converge as we delve deeper into the past. The flow of our light cone reaches a maximum size and then decreases again. Our past takes on a pear shape. The further we go back in time within the light cone, the more the positive energy density of matter causes the light rays to converge. The flow of the light cone narrows to zero over a finite time. This means that all the matter inside the light cone will end up in a boundary region that narrows to zero. Time must have a beginning as a result of the Big Bang. Similarly, it can be proven that time will not have an end when stars and galaxies collapse under their own gravity and form black holes. We have circumvented Kant's antinomies of pure reason by rejecting the underlying assumption that time makes sense independently of the universe. Meanwhile, Lifshitz and Kalatnikov found themselves in an awkward position. However, they found a way out by discovering a more general family of solutions with singularities that did not require the special stipulations of previous solutions. This allowed Lifshitz and Kalatnikov to assert that singularities, along with the beginning and end of time, do exist. The discovery by the Soviet scientists was not well received by most physicists. Thoughts of the beginning and end of time raised doubts among them. Therefore, they pointed out that one should not expect such a mathematical model to accurately describe spacetime in the vicinity of a singularity. General relativity, which describes gravitational interaction, is a classical theory and does not account for the uncertainty introduced by quantum theory, which governs all other known interactions. This mismatch plays no significant role almost anywhere and at any time in the universe, as the scales at which spacetime is curved are very large, while the scales at which quantum effects must be considered are very small. However, in the vicinity of a singularity, these scales are comparable, and thus quantum gravitational effects begin to play an important role. To understand the origin of the universe and what awaits it, a quantum theory of gravity is needed. However, when scientists attempted to extend the ideas of quantum mechanics to Maxwell's equations, which describe electricity, magnetism, and light, they initially failed. In 1865, British physicist James Clerk Maxwell unified all known laws of electricity and magnetism. Maxwell's theory is based on the existence of fields that transmit actions from one place to another. Maxwell realized that the fields transmitting electric and magnetic disturbances are dynamic entities capable of interacting and moving through space. The resulting synthesis of electromagnetism can be described by just two equations that define the dynamics of such fields. Maxwell derived the first great consequence of these equations. Electromagnetic waves of any frequency propagate through space at the same constant speed. The the speed of light. One can imagine that an electromagnetic field consists of a set of oscillations with different wavelengths. The wavelength is the distance between the crests of adjacent waves. The field in the wave oscillates from one value to another, like a pendulum. According to quantum theory, a pendulum cannot be in its ground state, which is the state of minimum energy, when it is pointing straight down and possesses minimal energy, because in that case, the pendulum would have both a definite position and a definite speed of zero. This would violate the uncertainty principle, which does not allow for the simultaneous precise determination of both speed and position. The product of the uncertainty in position and the uncertainty in momentum must always be greater than a quantity known as Planck's constant. Writing this number down every time is too tedious, so we denote Planck's constant with a special symbol, h, with a bar over it. Thus, contrary to expectations, the energy of the pendulum in its ground state or minimum energy state is not zero. Even in the ground state, the pendulum, like any other oscillating system, must possess some minimal amount of so-called zero-point fluctuations. This means that the pendulum is not necessarily pointing straight down. There is some probability that it is slightly deviated from the vertical. Similarly, even in a vacuum, the state of minimum energy of waves and the electromagnetic field is not zero. They can have some small amplitudes. The higher the frequency of the pendulum's oscillations or the frequency of the wave, the number of oscillations per minute, the higher the ground state energy will be. Thus, a straightforward assessment of the zero-point energy of the electromagnetic field and the electron field shows that the charge and mass of the electron are infinite, which contradicts observations. However, in the 40s of the 20th century, physicists Richard Feynman, Julian Schur, and Stephen Tyrrell developed a method that allowed them to systematically eliminate such infinities, subtracting them out and working only with finite observable values of mass and charge. Nevertheless, zero-point fluctuations still caused small effects that could be measured and were in good agreement with experimental data. Similar subtraction schemes that avoid infinities also work in the Yang-Mills field, a theory proposed by Chen-Ning Yang and Robert Mills. The Yang-Mills theory is a logical extension of Maxwell's theory. It unifies two other fundamental interactions, namely the so-called weak and strong nuclear interactions. However, zero-point fluctuations play a much more significant role in quantum gravity theory. Here, again, each wavelength corresponds to zero-point energy, as the wavelengths in the Maxwell field can be arbitrarily small. Every region of spacetime contains an infinite number of different wavelengths and an infinite amount of ground state energy. Since energy density, like matter density, serves as a source of gravity. Infinite energy. Density must mean that there is enough gravitational attraction in the universe to collapse spacetime into a single point, which evidently has not occurred. It seems one could attempt to resolve the apparent contradiction between theory and observations by claiming that zero-point fluctuations do not exert gravitational influence, but this would not help. The energy of zero-point fluctuations can be detected through the Casimir effect. If a pair of metallic plates is placed a small distance apart in a vacuum, it turns out that the number of lengths of electromagnetic waves that can exist between the plates will be slightly less than that outside. This means that the energy density of zero-point fluctuations between the plates, while remaining infinite, is less than the infinite energy density outside, and the difference between them, of course, the difference in energy density, provides a force that attracts the plates to each other, and this force can be measured experimentally. According to general relativity, forces are just as much a source of gravity as matter, so it would be illogical to ignore the gravitational impact of such a difference in energies. There is another possible solution to the problem: to assume that there exists a cosmological constant, similar to the one Einstein introduced into his equations when he was trying to create a static model of the universe. If the value of this constant were equal to negative infinity, it could balance the infinite value of zero-point energy in free space. However, such a cosmological constant would still be a tremendous stretch and would require incredibly precise tuning. Fortunately, in the 70s of the 20th century, a completely new kind of symmetry was discovered that provides a natural physical mechanism to balance the infinities arising from zero-point fluctuations. This feature of modern mathematical models of spacetime is called supersymmetry, and it can be described in various ways. In particular, one can say that besides the dimensions we observe, spacetime has additional dimensions. These are called Grossman dimensions, and since they are measured in numbers known as Grossman numbers, they are in ordinary real numbers. When you multiply real numbers, they can be rearranged, meaning it does not matter in what order you multiply, as 6 times 4 is the same as 4 times 6. In Grossman variables, as mathematicians say, they anti-commute. X times y will equal negative y times x. Initially, supersymmetry was viewed as a tool to eliminate infinities in material fields and Yang-Mills fields. In a spacetime where both the measurement in real numbers and the Grossman measurements are flat, they are curved, but it was natural to generalize them to the case where both real number measurements and Grossman measurements are curved. This gave rise to many theories of supergravity that required varying amounts of supersymmetry. In particular, from supersymmetry, it follows that every elementary particle must have a superpartner with spin either 1/2 greater or 1/2 less. The ground state energy of bosonic fields with integer spins 0, 1, and so on is positive, while the ground state energy of fermionic fields with half-integer spins 1/2, 3/2, and so on is negative. Since in supergravity, theories fermions and bosons are balanced, the greatest infinities cancel each other out, leaving the possibility that smaller infinities may remain afterward. No one has yet had the patience to calculate whether supergravity theories indeed lead to finite numbers. It is believed that the most diligent student would need about 200 years for this, and who can guarantee that they won't make a mistake on 2 pages? Yet until 1985, most scientists were convinced that overall, the theories of supersymmetric supergravity allowed for the elimination of infinities. Suddenly, the trend changed. Scientists declared that there was no reason to be confident that supergravity theories indeed do not contain infinities, and from this, they concluded that these theories are fundamentally inconsistent. Instead, they proposed another theory, the supersymmetric string theory. It was believed that this was the only way to reconcile gravity with quantum string theory. Just like ordinary strings we are familiar with, these are long, one-dimensional objects. Apart from length, they have nothing else. Strings in string theory move through a background spacetime. The vibration of a string is interpreted as a particle. If strings, in addition to the usual measurements represented by numbers, also have Grossman measurements. Then their vibrations correspond to bosons and fermions. In this case, the positive and negative ground state energies cancel each other out so precisely that no infinities remain, not even the smaller ones. Proponents of string theory declared it the theory of everything. In the future, historians of science will surely be interested in tracking how opinions among theoretical physicists changed over the years. String theory reigned supreme, while supergravity was dismissed as merely an approximate theory that only holds true at low energies. The term low energies sounded particularly hurtful, although in this context, low energies refer to particles whose energy is lower than that of a particle resulting from an explosion of trinitrotoluene multiplied by a billion billion. Since supergravity was merely an approximation for low energies, it could not claim the title of a fundamental theory of the universe. It was believed that a theory of everything could only be built on one of 5 possible string theories. But which of these described our universe? And how could one formulate a string theory if one moves beyond the approximation where strings were depicted as surfaces with one spatial and one temporal dimension moving through flat background spacetime? In that case, do strings not curve the background spacetime? After 1985, it gradually became clear that string theory does not provide a complete picture. For starters, scientists realized that strings are just one member of a vast class of objects that can have more than one dimension. Paul Townsend, a member of the Department of Applied Mathematics and Theoretical Physics at Cambridge, who conducted fundamental research in this area, called these objects branes. A brane has a length in pi dimensions. Thus, a brane with one dimension is a one-dimensional object, while a string with 2 dimensions is a surface or membrane, and so on. There is no reason to prefer the case of a one-dimensional string over all other values of pi. On the contrary, one should follow the principle of vibrational democracy. All branes are created equal, and all branes can serve as solutions to the equations of supergravity in 10 or 11 dimensions. It seems that 10 or 11 dimensions do not resemble the familiar spacetime at all. However, the main idea here is that the other 6 or 7 dimensions are compactified and so small that we do not notice them, while we are only aware of the other 4 large and nearly flat dimensions. I must admit that I personally found it difficult to believe in additional dimensions, but I am a positivist, so the question of whether additional dimensions truly exist does not make sense to me. It should be framed differently. Do the mathematical models with extra dimensions adequately describe the universe? So far, we have no observations that would require additional dimensions for explanation. However, there is a possibility that we may obtain such observations at the Large Hadron Collider in Geneva. Nevertheless, many, including myself, were compelled to take models with additional dimensions seriously due to the fact that there exists a network of unexpected relationships among the models, known as dualities. These dualities show that all models are essentially equivalent, meaning they are all different aspects of the same overarching theory, which has been dubbed M-theory. To consider the network of dualities as a sign that we are on the right track is akin to believing that God hid fossils in rock to mislead Darwin into an erroneous notion of evolution. The duality demonstrates that all 5 string theories describe the same physics and are physically equivalent to supergravity. One cannot say that superstrings and fundamental supergravity are one or the other. They are different expressions of the same overarching theory, each suitable for calculations in various situations. Since there are no infinities in string theories, they are good for calculating what results from the collision and scattering of high-energy particles, but they are not very suitable for describing how the energy of a very large number of particles curves the universe or creates a bound state, such as a black hole. For such cases, supergravity is needed, which is essentially based on Einstein's theory of curved spacetime with some additional types of matter. To describe the properties that quantum theory endows time and space with, it is useful to introduce the concept of imaginary time. It may seem like something out of science fiction, but in reality, it is a widely accepted mathematical concept. Time is measured in so-called imaginary numbers. Imagine ordinary real numbers, 1, 2, 3, 5, and so on, at corresponding points on a number line going from left to right, with 0 in the middle, positive real numbers to the right, and negative ones to the left. Then, imaginary numbers can be represented on a vertical axis, 0 in the middle, positive imaginary numbers on a ray going up, and negative ones on a ray going down. In other words, imaginary numbers are a new kind of number that is perpendicular to ordinary real numbers. Since imaginary numbers are a mathematical concept, I need a physical realization. One cannot have an imaginary number of apples or deposit an imaginary sum of money in a bank account. It might seem that this implies that imaginary numbers are merely a mathematical amusement with no relation to the real world. However, from a positivist philosophical perspective, one cannot determine what is real and what is not. One can only understand which mathematical models describe the universe we live in. Thus, it turns out that a mathematical model involving imaginary time predicts not only effects we have already observed, but also effects we have yet to observe. However, we have reasons to believe in them. So what is imaginary and what is real? Perhaps the difference is only in our heads. The classical, that is, non-quantum, Einsteinian general theory of relativity combines real time and 3 spatial dimensions, considering a single 4-dimensional spacetime. However, the measurement of time indeed differed from the 3 spatial ones. The world line of history, from the observer's perspective, always moves in the direction of increasing time, meaning time always flows from the past to the future. But in any spatial dimension, it could go either up or down. Thus, one can turn back in space, but not in time. On the other hand, since imaginary time is perpendicular to real time, it behaves like a 4th spatial dimension, thus offering far more possibilities than ordinary time with its linear structure, which has only a beginning or an end, or one can travel in a circle. Time has a shape, and it is in this imaginary sense. To assess some possibilities of imaginary time, let us imagine space-time with imaginary time as a sphere, like the surface of the Earth. Suppose that imaginary time corresponds to degrees of latitude. Then, the history of the universe in imaginary time would begin at the South Pole. There is no sense in asking what was before the beginning. This time is simply undefined, just as points south of the South Pole are undefined. The South Pole is a perfectly ordinary point on the surface of the Earth, where the same laws apply as in all other points. This means that in imaginary time, the moment of the universe's beginning could have been an entirely ordinary point in space-time, governed by the same laws as the rest of the universe. Another variant of the behavior of imaginary time can be imagined if we assume that imaginary time corresponds to degrees of longitude. All meridians, lines of longitude, intersect at the north and south poles. Thus, it turns out that time stops there in the sense that as imaginary time or degrees of longitude increase, one remains in the same place. This is very similar to how time stops at the event horizon of a black hole. Now we understand that the stoppage of imaginary and real time does not occur only for both simultaneously. This means that spacetime has a temperature, just like black holes do. A black hole not only has a temperature, it behaves as though it has a parameter commonly referred to as entropy. Entropy is a measure of the number of internal states, the ways a system can be organized from within, in which a black hole can exist without changing from the perspective of an external observer who only sees its mass, rotation, and charge. The entropy of a black hole is described by a very simple formula. Entropy equals the area of the event horizon of the black hole. For each unit area of this horizon, expressed in fundamental units, there is one bit of information about the internal state of the black hole. This indicates a profound connection between quantum gravity and thermodynamics, the science of heat, which also studies entropy. Furthermore, this suggests that quantum gravity may manifest in the form of the holographic principle. Information about quantum states in a certain region of spacetime can somehow be encoded on the boundary of that region, meaning in a space that is 2 dimensions less. This is akin to a hologram that contains information about a 3-dimensional image on a 2-dimensional surface. If quantum gravity incorporates the holographic principle, it likely means that we can trace objects inside black holes. Without this, it is impossible to predict what the radiation from black holes will be like. In turn, without such predictions, we cannot calculate the future as accurately as we would like. It seems we live on a 3-brane, a 4-dimensional surface, 3 spatial dimensions plus 1 time, representing the boundary of a 5-dimensional region, while the other dimensions are compactified and very small. The state of the world on the brain is a code that contains information about events occurring within the 5-dimensional region. The shape and direction of time in Einstein's theory of relativity, which is confirmed by numerous experiments, show that time and space are intricately interconnected. One cannot curve space without also affecting time. Therefore, time must have a shape. However, it seems that one can only move through time in one direction.